while we are waiting for the others. So who is afraid of mathematics?
I'm not afraid of it, but
That's our goal. So that you're not only not afraid, but you understand what we're talking about. Because without understanding, all this doesn't make any sense. So my goal is, as a course instructor, is that you have the understanding of everything that we're talking about. In that case, it's better to cover less than not to have an understanding of what. So that's why we need to decide whether we do a review of Python or we skip that, as pretty much you already either know how to program in Python, or you take the preparatory course, or you may have taken online courses, but everything else we will be covering. So this is something that we'll now need to decide whether we want to spend an hour reviewing Python or we skip that.
my preference would be to do Python on my own. There's lots of resources for Python, like I don't, it's not specialist, so.
That's why I put it optional, So there is all the tricks I will be showing you in the Jupyter notebooks that you need, but spending time on this review of Python doesn't really make much sense.
And you also had the pre-course,
And you had the pre-course, and basically part of your mark is 20% of your mark is the knowledge of Python, which can be improved in a number of ways. If you have taken the pre-course, it's enough. You can take online courses and show that you completed those to Katerina, our TA, or we can arrange any other way to prove that you know Python so that you get this 20% of your mark for Python. So in that case, it makes sense to skip this review of Python. If you want, there are slides and handout posted on Moodle. So where we stopped here, we stopped at overview of the data science and AI algorithms, and because we no longer have MDT students, we will go into more details of those in any case later on. So in that case, I'll start with a review of basic statistics, and again, we probably need it to be on the same page, even so you had a course in statistics. But I would like to spend this 1 hour and 20 minutes on the review of statistics so that we, as always, we understand what we are talking about, and of course, how to do it in our case in Python. So you use Bar for the statistics course. So that's in that case, jump to Python review, we'll jump to the basic statistics slide, because essentially statistics is the first type of data science algorithms that we are going to be working on. So, why statistics? So statistics first is basically what we need to start analyzing data, and some of the simplest algorithms in data science are the statistics algorithms, like hypothesis testing. That's already a data science algorithm that allow us to make decisions. So, for the statistics, we use statistics before we even analyze our data, just to look at the data, understand the data. We need to understand sources of uncertainty. We need to understand what type of data we have, whether it's quantitative data or categorical data. We need to understand what are distributions, and we need to understand some of the important questions from statistics, such as hypothesis testing, law of large numbers, and central limit theorem. Again, from practical standpoint, how we apply all this to data analysis. And before we even start analyzing the data, we need to understand where our data is coming from. And the major thing, do we have access to a complete data or a sample? Or in statistical terms, do we have access to the population or just a sample with your code in Ukraine? And to answer that question, we basically, typically again, we have access to a sample only. In some cases, so examples, the complete data set, if you have the entire database of sales transactions, that's a complete data as a population. But if you only have, if you start collecting transactions only from last year, that's already a sample. Before that, we didn't collect the transactions. So for the sample, we need to answer the question how the sample was collected. Was it collected randomly, or where is the dependence in how the sample was collected? And this is a big thing. So, and that determines about what we can make conclusions. So, for instance, if we have a complete immigration data of the New York City users of the web service, can we make conclusions about all New York City users of the service, or we can make conclusions about all New York City inhabitants? And the answer is, of course, we can only make conclusions about the New York City users of that service. We cannot make conclusions about all people living in New York City. because that sample that we have access to, the demographic data of the users of this web service, is really it's not randomly selected. There is a dependence between those people. We are all using this web service in the city. So this is, I tend to explain it based on the election polling. So election polling is probably one of the very cool uses of statistics in data science. And we all know about the last presidential election in the United States. So, anybody knows how election polling is done? Як опитування робляться перед виборами? Anybody heard that they report? So we basically, we sampled 1,000 people and the margin of error is 3%. So blah, blah, blah. Anybody heard of that? Those type of numbers, typically reported statistics. So the question is, why margin of error is 3% when we sample 1,000 people? That's what we'll know by the end of this lecture. And second, how do we make sure that it's really 3% and not more than that? How do we know about that? So for that, of course, a couple of things that we need to make sure that the sample that we're working from is random and representative. What do we mean in the election polling representative? So it represents all people living in that country, all voters, living in different cities and villages, representing different social groups and so on. So representative. Random, we really sampled random people. What does it mean, random people? So in the past, how you do election polling? You were calling people on their landline phones, yes? That's how election polling was done for the last 60 years. You call people on their landline phones and you ask them whom you're going to vote for. What's wrong with that idea at the moment?
It's not really random.
It's not really random. So if you call a landline phone, домашний телефон, who is going to pick up the phone?
Granny.
Exactly. All people are going to pick up the phones, and as a result, you're not polling all people, you're polling older people. So there is a dependence in your sample. Вибірка є залежна. Everybody with me on that? So, the technology that was the cheapest and worked for 60 years, since every person, I think every family, every household in the United States had the landline phone since the 50s. So that broke down around 5-6 years ago. And the first reason is, yes, people start getting mobile phones, and people who keep the landline phones are typically older, so as a result, you automatically, having that your sample is no longer random, you are sampling all the people. There is a dependence in your sample. So, and you cannot make a conclusion about how average voter is going to vote, you can only make a conclusion how all the people are going to vote. But that's probably not your goal. You want to know how all people are going to vote, not only all the people. That's one problem. Second, you can try to get phone numbers of the mobile phones and call people on the mobile phones, and everybody is trying to do that in the US, in Ukraine. The problem is, if you're getting a call from an unknown number, are you going to pick up the phone? Not necessarily. Again, another dependence. So people tend not to pick up the phone, the mobile phone, if it comes from an unknown number that you don't have in your contacts. And that was really, those type of problems were identified as problems during the polling of their last presidential election campaign in the United States. And that's one of the explanations of why every polls were underestimating the probability of Trump winning the election. So there are people who voted for Trump, those are the protest people, so there is an additional dependency. When you call those people on the mobile phones, there is a higher chance that they're not going to pick up the phone, because they're everything. So that's what it is. And so as a result, after the last presidential election, after the election day, there were all these publications in Wall Street Journal, the New York Times, that bad election day forecasts still go to data science, how data failed us in calling an election, and so on. So pretty much people would think, what happened? So all their pretty much election polls, and this is one of the polls, BBC polls of polls, were predicting that on the election day, there 48% for Hillary, 44% for Trump, that we got Trump winning the election. And of course, partially it had to do with the electoral system in the United States, which makes it more difficult to do election polling as compared to Ukraine. So anybody knows on the high level what is their electoral college system in the US?
general.
Yeah, let's go to it because it's useful to understand the complexity of doing data science when election system is not how it's called in Ukraine. Basically, in
Direct.
probably direct. So in the United States, so the results are by every state. So what happens? So first, people go and vote in every state, and if people voted in every state for one candidate, all electoral votes from that state go for that candidate. Each state has a number of electoral votes, so total number of electoral votes is, well, you need to get to 170. So total number, I think, is something like 500, yeah? So total number of electoral votes for each state is proportional to the number of people living in that state. So for California, it's the largest, 55 electoral votes. Florida 39, and I think Hawaii is like 3. So if more than 50% in California voted for Clinton, all 55 electoral votes from California will go for Clinton. If more than 50% vote for Trump, all 39 electoral votes from Florida will go for Trump. And the president needs to get 270 electoral votes in order to win the election.
Some states give proportional votes though, right? It's not all.
I think it's 2 states only,
Yeah,
so that's why people typically disregard those. Yeah. So as a result, first what you need to do, you need to really sample people in every state separately. You cannot sample on the country level in order to predict the election, which is more expensive. So you need to do it state by state in the United States. In Ukraine, you can do just the whole country at once, which is less expensive. So that's another difficulty in the electoral college system. So всі голоси виборщиків від цього штату йдуть до кандидата, за якого проголосувало більше 50%. And now coming back, so those are the types of problems that appear during the election. Low response rates. Even if you call a person on the phone and the person picks up, so the person has low rates of picking up the phone. And people picking up the phone is no longer a random event. In the past, if you call the landline phone, people are not picking up the phone if they're busy doing something else. Now you can pick up the phone because you don't want to pick up that number, and that's a dependence. Inadequate coverage. So to cover all the states, it's in the US, it's really expensive. Hidden dependence. Who tends to answer the phone? So yeah, if it's a landline, that's all the people, and so on. Other questions that you design, how you ask questions. If you ask directly whom you're going to vote for, you're not going to get the true answer. People tend not to reveal their true answer. So you need to design questions in such a way that people reveal their true preferences. But in addition to know what that person is going to vote for, you need to figure out if that person is going to go and vote. If the person is not going to go and vote, his or her answer is irrelevant. So you shouldn't count that person. So design of questions for the surveys, this is really important, and we will have a course about that from Natalia Pertsurka. So design of surveys and market research. So that's another important thing. If you get data from surveys, you need to be able to design questions in such a way that people reveal their true opinion. Because otherwise you have this dependence, and you need to design incentives for people. My favorite example probably, so if somebody asks you to fill a survey that takes you half an hour, and you get a $5 Starbucks gift card for that. So is it going to be an independent sample or dependent sample?
Or dependent.
Yeah, it's dependent first. You're probably going to poll people who value Starbucks, who like Starbucks, so that they want to get the gift card. Second, the time value of money for those people is so $5 for half an hour, $10 per hour. So people who are earning $10 or less per hour are going to fill the survey. People who are earning more than $10 per hour, so they are not going to fill the survey because they would get more money doing something else. So there is always these things of dependencies when you design the surveys. And again, so their methodologies and the people who are doing the surveys, they also tend to lean one side or the other, so they can interpret answers differently. And their opinions in the polls are historical text, because the polls done prior to the election, not at the election day, so people's opinion can change. So all these difficulties make the polling really difficult right now, and that's part of the reason we'll revisit it at the end of the election, why the election results were really predicted differently, because the true margin of errors were not 3%. They were much, much higher because of those dependencies. Even if you sample 1,000 people, but you have all these dependencies and your sample is no longer random and representative, your margin of error will be much higher. And in the last election of in the S, those were probably around 10%. And when you have 10%, so you cannot really say much. So in this case, of course, 44 plus minus 3% and 48 plus minus 3%, that tells you something. But 44 plus minus 10%, that's probably the complete overlap of these two. So just to write this down. So if you have, here is 44, here is 48, and when plus minus 3% margin of error, so you have something like this, and the overlap will be around 15% here. So what it means, 85% chance that Hillary win, 15% because of this overlap that Trump win. That's what most predicted. But if you have plus minus 10%, so pretty much you have something like and something like so the overlap is, let's say, close to 50%. In that case, it's pretty much 50-50. And that's what really happened. So the margin of error was not plus minus 3%, but plus minus 10%, and as a result, the polls were not really us that much. It wouldn't be a problem if the difference was not 44-38, it was 40 and 60, of course, plus minus 10% is still okay, and you still know who would win, but because the candidates were so close, the margin of error should be really small in order to make any conclusions from this. Still puzzling? Yes? No?
It's also true that the polls could be perfectly correct, and also that's the correct, that result happens too. Like,
Yeah, if people change their opinion
no, even if it's correct,
close to the elections.
margin of error is there for a reason. You know?
Yeah, margin of error, but at least you know. So if those margin of errors were correct, it's really 85% for chance of Hillary winning and 15% for Trump. Still, of course, 15% is not that much, so Trump can still win, but with this, it's pretty much it's much more certain. It's almost 50-50. Okay, so that's, again, those simple things that what statistics tells us, and we should take all this with a grain of salt and have the understanding of what's going on. So, next. So we need to understand what type of data we are dealing with, quantitative, numerical, those are numbers, or categorical, so categories, like male, female, and categories can be ordered or unordered. So for data collection, as I told, so we would like to have independent observations. So if there are dependencies, we should understand what are the dependencies in our data and how we get rid of those. So even before we start analyzing, we should plot our data. We should summarize our data with statistical summaries, and only after that we can start running algorithms and make conclusions and issue predictions. So first, understanding data using statistics is really important before we start running more complex algorithms. And again, one more summary about complete data versus sparse data. So when we have complete data, which happens very, very rarely, census, say a quick census.
Referendum.
Census, in theory, is a complete data set. Database of all business transactions is complete data. Big data, as I said, this airline example, when you have the prices of every flight, that's a big data. In some cases, we can have it. But in most cases, we have access only to the sparse data, survey data. It's not a population, it's a sample. Sensor data, it's a sample because we are not collecting sensor readings every millisecond. We're collecting it every minute, every 2 minutes, still sparse data. Experiments, sparse data. And of course, when we have access to sample versus the complete population, it's a greater uncertainty in the data. Because our goal is, based on a sample, to make a conclusion about the whole population. The same, based on the sample of the polling, make a conclusion about the population voting, who will win the elections, so how the population will vote in general, and we try to infer those conclusions from a sample. And that's our typical data science flow. We have access to sample that we collected, and we try to make conclusions about the whole population. Сміло ми маємо вибірку і хочемо зробити висновки, як буде себе вести загальна сукупність, так називається. Because otherwise having access to the complete data is typically expensive or just impossible in general. And that's why we have to work with samples in most cases. Not always, we still have some exceptions. And in addition to uncertainty from the data collection, they would have uncertainties in the model itself. So that's what we understand. Those are the sources of error in our predictions. Coming from data collection, sample, dependence. In the sample plus, when we come to the models, there is also uncertainty in the model. But with those, we have some good ideas how to deal with. Now, two types of data, as I said. Quantitative data. So this is example temperature, age, income. So if you ask a question, does it make sense to compute the average? And the answer is yes. You are working with quantitative data, which is also called numerical. So that's just числа, numbers. So for this, what we do, we first compute summary statistics to understand our data for the numerical data. Before that, we do the plots. And after we compute the summary statistics, we compute the mean and median, standard deviation, percentiles, before we go to run the more complex models. So those are typically called one-number summaries. So mean is just the average, summing up all the numbers in our column of data and dividing by the number of observations. The median is the center value, so the 50% of our data is below the median and 50% of our data is above the median. So what we need to do with the median, we just sort out our observations from the smallest to the largest and take the observation in the middle, and this is the median. But these one-number summaries do not tell us a complete story. Because let's say that we did a plot of our data and it looks like this. Everybody can do the bar plot, I guess. Everybody can do the bar plot in Python of our data. If you have a column of data in Excel or in Pandas data frame, everybody can do the bar plot of that data. So after that, as you see, let's say we have two data sets, this one and this one. And when we compute the mean and the median, those are 19.8 and 18.8. As we see, these numbers do not tell us a complete story, because our data set can be different, and if we just disregard the plot and just look at these numbers, we are missing some information. Everybody agrees about that? So which information we are missing in these two cases? Yeah, we're missing information how spread is our data around the mean, which we typically call variance or standard deviation. But another interesting observation is probably very intuitive. So if the mean and the median are very close to each other, quite close to each other, what we can tell about the distribution of our data?
Normal.
Why normal? So we cannot tell that it's not.
No.
It's normal.
That there is no outliers.
We can only tell that it's symmetric. Again, it's not necessarily normal. Gaussian is the same as normal. Just another name for the normal distribution. So here, all what we can tell if this median and number are approximately the same is the distribution is symmetric. It's not all symmetric distributions are normal. If the mean and the median, as here, are not close to each other, our distribution has a fat tail, and this typically, that's probably the Ukrainian equivalent. In this case, the fat tail happens to be on the right, the distribution is skewed to the right, and there is a fat tail. In this case, the mean is greater than the median. And for some data set, basically, why in many cases, instead of showing the distribution plot, people report one-number summaries? Because for most people, it's much easier to interpret numbers than to interpret some complex object like a distribution. So that's why in newspapers or anywhere in the news it's written, average, on average, blah, 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 median, blah, blah, blah. And for some cases, it makes sense to report the mean. For some cases, it makes sense to report the median. For instance, for the income, what if you report the income of people in Ukraine, for instance? What it makes sense to report, the mean or the median?
Median.
Why median?
Because there are some very rich people, yeah.
Exactly. There are some rich people which will drive the mean to the right. So in this case, for instance, because of this small number of rich people that have very high salaries, so the mean is whatever, 19,000, 20,000 per year, but the median is 10.5. So the median, what it tells us that that half of the population earns less than 10.5, half of the population earns more than 10.5. So the median is more interpretable when we report the income. In other cases, reporting the mean is more intuitive and makes more sense. And again, all these reporting numbers instead of distribution is simplified. As people, we tend to have difficulties working with multidimensional objects such as a distribution. Numbers are much, much simpler because we can compare numbers. We cannot compare distributions. If I tell you to compare distributions, you will need to think what I do to compare distributions. And if I tell you, let's compare the means, well, the two numbers is very easy. So again, very simple intuitive things. As people, we're good to compare and work with numbers. We are not good to work with more complex objects such as distribution. Even the ranges of numbers is more difficult to work with than the numbers itself, because there is no easy way to compare ranges or to compare distributions. That's why for reporting, we typically simplify, we just report the numbers, and that may allow us to miss some of the important information if we just report one number summaries. Another interesting things about this, as we talked about, so this type of distributions are called fat tail distribution, and typically interesting things are happening in the tail.
I think it's long tail.
How you tell it's long tail?
No, long tail, not fat tail.
Yeah, some people probably tell long tail, some people tell fat tail. Yes, it's probably the
I think
same.
it's long tail. I remember.
In Canada? Because I typically hear fat tail, yeah.
Okay, long tail. Okay.
I will need to check. So British English, American English, Canadian English, Australian English. Top stick list. In Ukraine is probably fat as well. Maybe. Well, we need to ask Tatiana Marinich, who is much better in statistics than I am. And as we already mentioned, so these type of events in the tail are called black swans. Coming back to the same after the book of Hassim Nicholas Taleb, black swan, Chorny Lake. So why these type of events that we see in the fat tail of the distribution are called black swans? Again, those have three properties according to Taleb. So first, they have a small probability, and as expected, everything which is in the tail has small probability. Second, they have large impact. Those people who have high salary have large impact. And third, Taleb claims that it's almost impossible to model those events. Even so in data science we try, so I would rephrase it, it's difficult to model those events in the tail because those are rare events. We are not necessarily able to observe those in nature. And that's why actually those are called black swans. So the history of this black swan is, so before 19th century, all swans, sea leopard, that we observed were white. And after that, in 19th century, somewhere in Australia, we found the black swan. And that was a black swan event because that has all these characteristics. So it's a rare event, has small probability. Until 19th century, nobody has seen a black swan. It has a large impact, potentially on zoology, on people studying zoology, and it's difficult to predict, almost impossible to predict that you can somewhere find the black swan. And this is really the core, in many cases, of the model, to be able to predict rare events. This is the core of modeling in climate change, in weather modeling, in financial markets, and in many other areas of data science. If we interpret this distribution as a distribution of the losses of my financial portfolio, again, those are the events that Taleb called black swans, because those events are very, for instance, those are events of the defaults of large banks, where my portfolio loses a lot, when some of the banks or companies go bust. Again, losses are huge in my portfolio, those events are rare, and it's difficult to model those. The same for natural disasters, earthquakes. Distribution of earthquakes, magnitudes will have this type of shape. The high magnitude earthquakes are rare events, have large impact, and difficult to model. So this is important to basically understand. And so, as I said, it's misleading to report only one number summaries. When those are reported in the newspaper or somewhere else, it's a misleading information. And that's called the flow of averages. And there is a whole book of that by Sam Savage, where basically he tends to explain this, the main idea that plans based on average assumptions are wrong on average. Because if we know that the average depth of the river is 3 feet, which is 90 centimeters, I believe, and you based on that assumption, plans based on average, you make a decision to cross the river, it doesn't tell you if there are such pockets in the river and you may get drawn in the river. So plans based on average assumptions are wrong on average. That's, when you work with data, you need to look at other properties of the distribution, at other one number summaries in addition to the mean or the median. Because these two distributions have the same mean, but look completely different. So if you just rely when making a decision on the means, you're losing a lot of information. Everybody with me on that? Again, important to understand and remember this picture. So that's why, in addition to computing means, medians, and modes, we also need to compute and understand standard deviation. So what is standard deviation? Is a measure how spread is our data around the mean. That's all. And that's what this formula says. This x bar is the mean, xi is individual observation, so we compute the difference between the individual observation and the mean, squared, sum up, divide by n minus 1 if you want to make it unbiased and take the square root. So this is standard deviation. Without square root, it's a variance. And how we interpret this standard deviation, so there is a rule of thumb, so which says most observations fall within plus minus 2 standard deviations of the mean. So what do we mean by most? Typically around 95%. And basically this rule will be completely correct if our data is normally distributed. Otherwise, it's typically only approximately correct. But that's the rule of thumb. So 95% of observations fall within plus minus 2 standard deviations from the mean. So if we basically put it projected on this data, which is not really normally distributed, but quite close. So what the mean is 19.8, standard deviation 4.2. 19.8 plus minus 2 multiplied by 4.4, so we get this range that approximately 95% of observations are between 11.4 and 28.2 plus minus 2 standard deviations from the mean. Again, that's a rule of thumb that we typically rely in statistics and again to interpret and understand the data. And that actually brings us to the distributions. You talked about the distributions in the statistics course. It's important to understand the distributions. And the most popular distribution, as you already know, is the normal distribution, which is also called Gaussian distribution. Why? There are at least 3 reasons why normal distribution is important in data science. Okay, let's try to get those. Any ideas why normal distribution is used so often and why it's so important?
To guess probability.
You get probability from any distribution. Well, random variable can have any distribution, not necessarily normal.
That allows you to go from sample to population with some predictability.
Okay, so that's one reason, and it's called central limit theorem, which we'll discuss, and we'll probably discuss it. Yes, what central limit theorem tells you that the means, if you want to make any decisions about the averages, how people vote on average, exactly the decision what we would like to make in election polling. So the distribution of the means, sample from any distribution is going to be normally distributed. That's what central limit theorem is telling us, and we'll review central limit theorem. So don't worry if you still don't grasp it completely. That's one of the reasons. Central limit theorem, because if you make decisions about the averages, how people behave on average, and so on, you will work with normal distribution due to central limit theorem. First reason. Any other reasons? So one reason is directly on this slide.
I think that just
Symmetrical?
No, that's practical reasons. So you see what is, so that's the height of the person.
yeah.
The height of a person is normally distributed. So many physical processes that we found in nature are normally distributed. And probably this understanding the height of the person. It's normally distributed. Many other processes in physics are normally distributed. And the third reason is it's easy to work with normal distribution. So to plot this curve, so how many numbers you need to know? We already mentioned what were these numbers.
1 sigma, 2 sigma, 3 sigma, 1. Yeah.
Mean and standard deviation. You just need to know 2 numbers, and after that you can plot this function. So when you know the formula of the science, exponential function minus blah 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 minus x minus mu squared divided by standard deviation, things like that. So this curve, this bell-shaped curve, which is called the bell curve in many cases because it's like conical, the bell. So this, it's easy to work with normal distribution. You need to know 2 numbers to work with it, and it's nicely extends to the multi-dimensional space when you need to interpret, of course, correlations, covariances, but still you can do that.
А если майор, то что? Я могу предоставить?
So another, coming back to interpretation of the normal distribution, so the area under any distribution is 1, yeah, 100%. That's what we also know from statistics. So plus minus 1 standard deviation. Here is area 68%, plus minus 2 standard deviations. We have area 95%, plus minus 3 standard deviation. The area is 99.7%. So what that means, to find a data point which is more than 3 standard deviations from the mean, it's almost impossible. So the chance of that is what? 0.3%. Very, very small. Everybody with me, so some people call it the law of 3 sigmas or the law of 6 sigmas, but doesn't matter how it's called. That's what it is. This area of plus minus 3 standard deviation is 99.7%. So events, if your data is really normally distributed, finding an event which is outstanding more than plus minus 3 standard deviations is almost impossible. And that's give us immediately one of the algorithms for the outlier detection. If your data is not distributed and you have a point which is more than plus or minus 3 standard deviations from the mean, that's an outlier. Again, immediately gives you a data science algorithm how to identify outliers. And identifying outliers is one of the important algorithms in data science because in many cases, so this is also called anomaly detection, so we want to detect abnormal behavior or, in our data, for instance, to identify fraud. Fraud is the anomaly, it's abnormal behavior. So if we have something outstanding plus minus 3 standard deviations, if our data is read or received, that may be a fraud. Again, so some algorithms are based on that. Not all, of course, data is normally distributed. So this is a distribution of the wave height in the ocean. And as we see, so on average is what, like, I don't know, 2 meters or something. But there are some black swan events. Again, we have the fat tail of this distribution. So the waves with 12 meters high, 11 meters high, 10 meters high, 9 meters high, 8 meters high are very rare, but they have all the characteristics of black swan. Small probability, large impact. Yeah, because if they as high as whatever, 8, 9, 10 meters, that's a tsunami. Pretty much it will wash out everything from the shore. So, there are many cases where our data is not only distributed still as well. But typically, when you do your modeling and your data is at least approximately symmetric, you may start modeling from normal distribution assumption. We'll see that as well. So after that, now let's look at basically a data set, so which I also have in the Jupyter notebook. So we'll look at it there. So we have a data sample of 5,000 customers of our credit card company, and again, we make sure that this sample is random and representative, so you don't have to worry about that. And of course, we want to make conclusions about all customers of this company from this sample. So when we did this sample, we made sure that this is random and representative, so that we can nicely run our statistical model. And when we start looking at this data, so what we have, so in this data set we have more than 30 columns of data, but we'll be looking only at the 2 amounts spent on the primary credit card last month and the debt to income ratio. So debt to income ratio is income, debt divided to income, and that's in percentages. So first, when you start doing your modeling, you just compute your one number summaries, mean, median, standard deviation, minimum and maximum, and you plot your data as a bar plot to see immediately, oh, okay, this is approximately symmetric, we may potentially model it as normal, this is not symmetric, so debt to income ratio has fat tail, so we should pay attention on those people who are highly in debt because those may default. And it will be difficult to get money out of those. In addition to means, medians, modes, standard deviation, there are also percentiles. Did you cover percentiles in the statistics course? Yes, that's another way to provide one number summaries of distribution. First, median is the 50th percentile immediately, but it can be any other percentile. So the percentile is the data point below which P% of the observations fall, and this is in many cases used to report the standardized test score. So if you scored in the 93rd percentile, your score is higher than that of the 93% of test takers. Child growth percentiles are reported also as percentiles. So we can add percentiles to the picture. So the minimum is 0th percentile, of course the maximum is 100th percentile, 50th percentile is the median, 25th percentile, and 75th percentile here. And if it's useful to look at the percentiles, because if you look at the percentiles, you can immediately at least have an idea whether the distribution is symmetric or not. In this case, what you see, okay, so the maximum is 43%, the median is 9, and here we have the minimum is 0, so you know that your distribution is not symmetric because 9 minus 0 is 9, but so 43 minus 9 is much bigger. So the distribution is really has a fat tail. So without even plotting distribution, if you just look at the percentiles, it gives you enough information to make some conclusions about the shape of the distribution. And after that, we can start quantifying uncertainties in our data. why we basically want to do that. So what this confidence interval are telling us really? As I said, our goal is we have access to a sample, we want to make a conclusion about the whole population. And that's what confidence interval is telling us. So what we can conclude about the mean of the whole population when we have access only to a sample. That's all what confidence intervals are about. So, for instance, in our debt to income ratio, the confidence interval for the mean is 95% confidence interval is the mean is between 9.8% and 10.1%. What that means? So we are 95% confident that the average debt to income ratio for the whole population is between 9.78 and 10.14. And we made that conclusion from a sample. We compute this confidence from a sample, but we know that the population mean with 95% confidence is in this range. That's what confidence interval is telling us. We are trying to make conclusion about the mean of the whole population based on access only to a sample. Yeah, it's kind of mind-blowing, but in statistics, that's what we want to do in inferential. We want to infer or make conclusions about the population based on a sample. That's basically the core of statistics. Everybody with me so far? Маємо доступ тільки до вибірки, яку ми зібрали там в якому сервері, і хочемо зробити рішення по всіх людях, там, які є в нашій компанії, а маємо тільки вибірку. That's what statistics is about. Being based on limited data on a sample, as soon as we make sure that it's randomly representative, make conclusions about the whole population, about the entire population. Confidence interval can also be represented as a margin of error, because that's pretty much the same, just the margin of error will be, so in this case, so what we have the mean of 9.96 plus minus a margin of error of 0.18 and give us the same confidence interval. So confidence interval is margin of error, is the mean plus minus the margin of error, and then give us a confidence interval. So it's the same interval, just two different ways to report it. Either as an interval from this number to that number, or as a margin of error, mean of 9.96 plus minus the margin of error of 0.18. And again, that's another interpretation. So as we are talking about the mean, so we are here comparing the mean for the population and the sample. We know that means are normally distributed from central limit theory, as we will see. And that's why we can really see this result from the normal distribution. So what it's telling us, in this case, mean is 10.3. So margin of error is 1%, which is equivalent to 2 standard deviations. And so we know with 95% confidence, our margin of error is 10.3 plus minus the margin of error of 1%, and this gives us this confidence interval. Again, this area is going to be 95%, plus minus 2 standard deviations. Here is 2.5%, here is 2.5%. That's how we interpret their confidence intervals. So this is a distribution of what? This is a distribution of the mean of the population. This number is the mean of a sample. Yeah? And we know that with 95% confidence, the population mean will be in this range. So between this number and this number. Sample mean plus minus the margin of error. That's a confidence interval for the population mean. Yeah, this takes time to digest. Just always remember that that's how we typically do modeling. We have access to sample, we try to make a conclusion about the whole population. In this case, we are quantifying the uncertainty for the population mean, and how we quantify it by giving a confidence interval or the margin of error, which is the same. And the answer why we work with normal distribution, because we are interested in the mean. And the distribution of means computed from any distribution is going to be normal from central limit theorem that we still have to review. Questions? I don't know. Was it covered in the statistics course, these type of things? Just, yeah, our goal is to understand, so I'm not going to go into all details that Tatiana went.
I had to highlight myself, because we started with complicated things in statistics, but didn't look at such basic things, which actually I think we missed in
Yeah,
That's why another good thing is that in many courses you will have to look at the same things from different angles, and that's typically very rewarding in my opinion. So when we talk, I typically tend to look at statistics from a data scientist point of view. Tatiana probably look at statistics from statistician's point of view. And if you hear about these things from 3 different people in 3 different courses, even so it's a bit of a repetition, my opinion is very, very useful because you combine this understanding from different points into the complete picture.
yeah, like the relationship between margin of error and confidence interval is very obvious on this diagram, and we approach it just purely mathematically.
Okay, always let's think about distribution. So understanding the distribution concept is very important. So when we work with random variables, we work with distributions. We don't know what the price of, as I said, of IBM stock is going to be tomorrow. That's a random variable. We don't know what the temperature increase is going to be due to climate change. That's a random variable. The same here. So the mean of the whole population is a random variable. And this is its distribution of that random variable, which is the mean of the whole population. That's another way to look at it. Mean of a sample is not a random variable, that's a number. We have access to a sample, to all these numbers in the sample, so that's a number. But mean of the whole population, we don't have access to the whole population, it's a random variable. Another way to think about everything in this sense is random variables. Even so, I typically find it more.
But is it because we don't know the whole population ever? Because the life is continuous.
That's right. If you know the whole population, your mean of the population is no longer a variable, just a variable, just a number.
Even height in your example.
The height. Can you have access to the whole population? Can you ask every people in this world about their height?
Even if we can, then tomorrow you add more people.
Exactly.
New people are born. Somebody is dying. So you always have a sample.
That's random. You have a sample, but from that sample you can model quite precisely the population of the height of the population, and that's what it is. And that can be actually first, as we started talking about, can be a first model. So, how we can use all the statistics in data science modeling. For instance, you are Andrew Tan, and you're in the business of making suits. Yes. So for that you need to know which sizes of suits you want to make. For that, you need to model the distribution of the people height so that you can understand how many suits of this size I need to make, how many suits of this size I need to make. So, what you can do, and now let's solve a practical data science problem we should go and sell to Andrew Tan during the break. And that's a designer in this field. I guess I don't know much about him, all what I know this is famous designer because he's on the 3rd floor between 2nd and the 4th, everybody's talking about him at Kyiv School of Economics. That's my limited knowledge about Andrew Tan, and ladies can correct me, they probably know much more about him than we do. So, that's his problem. Now, let's probably simplify that he's only doing, is he doing what ladies and gentlemen suits or just let's say both. We don't. So now he decided he's basically
somewhere in the middle.
He needs to model the height of the people. That's his random variable in order to make different sizes. And after he knows that, okay, so if the size is here, this is, so if the height is here, this is size 1, this is size 2, size 3, and so on, 5, 10 different sizes. So corresponding, this is different sizes. So as soon as he's able to model this random variable height of a person, he knows how many different sizes of suits to produce. So here you measure this area, and okay, so this is 20%. So I need to produce 20% of size 1. Here is 15%. I need to produce 15% of size 5 and so on. Everybody with me? So again, oversimplifying. So random variable is the height of the person. After that, if you are able to model that, you can convert it into sizes and you know how many suites of each size you need to produce for the general population. So that's what he can do. So he can just, okay, you know that the height of the person is normally distributed. We know and figure out the mean and standard deviation. To plot this, we need 2 numbers. Again, by sampling people on the street in front of the building or sampling his clients from the past, whatever. We get these 2 numbers, the mean and standard deviation. We build this distribution, and after that, you know the ranges of the height for each size. After you compute these percentages, and you know how many slits of each size to produce. And so, again, very simple modeling. Something like that is still used, but with some adjustments. But then again, and that's just because here we need to do the uncertainty model. So we model random variable the height. We get the model, normal distribution, find the mean standard deviation. After that, we convert it into practical decision about the sizes. So you know the sizes, you compute each area, and you know which percent of each of the sizes to produce. Yeah, some of the tasks will be as simple as that. Modeling of demand and supply. That's how it's done in the simplest case. Typically, of course, the random variable will not be as simple. You may need to compute functions of random variables and so on. Okay, just 30 minutes. Now, next step. We quantify the uncertainty in population versus the sample. Now, next step. So the major statistical algorithm is hypothesis testing, which is all based on the same distributional assumptions that we make. So in hypothesis testing, we typically want to compare two or more groups, for instance, males and females, and make a decision whether these two groups behave. It can be three groups, of course, four groups, but in the simplest case, two groups. Whether these two groups behave similarly, or the same, or different in the population. Again, we still have access to the sample only. But in the hypothesis testing, we want to compare, on average, these two groups behave the same or differently in the population. And that's what is called hypothesis testing. For that, in this case, for instance, we would like to compare males and females, two groups. So we have almost half and half of those in our data, in 5,000 data points, 2,500 males, 2,500 females, and we can compute the means of these two groups for our debt to income ratio and for the amount spent on the primary credit card. As we see, okay, for the means, typically it looks like from our sample that on average debt to income ratio is higher for the females, 9.98% versus 9.92% for males. And for the amount spent on the primary credit card is the opposite. The men tend to spend more on average, $356 versus females $323 on their primary credit card. Now we want to understand, is this difference statistically significant, and the same for here, is this difference statistically significant in the population? If yes, we make one sort of decision. If no, we make another sort of decision. For instance, if this difference in the amount spent on the primary credit card is significant, so which means that men spend more than women, so we can treat these groups differently. For instance, if we propose a new credit card, we first propose it for men, because they bring more money to our company. Everybody with me? If these groups behave statistically the same, doesn't matter, we treat both groups the same. We propose new credit card to everyone. Everybody with me on that? And this is how all marketing is based on that. So if you think about promotions, marketing, pretty much, that's how they do it. They just compare two groups, can be males, females, can be by age, maybe more than two groups. And after that, they decide whether to treat these two groups differently or the same. Other people may call it, so it's slightly misleading term, clustering, segmentation. Customer segmentation is all that. You segment into groups, and after that you check statistically whether these two groups behave the same or differently. If they behave differently, you treat those differently. Design different promotions, different marketing campaigns for groups. Behave the same is the same promotion for both groups. Why that works? So now, in our time, if you want to do a marketing or promotion campaign, you have two choices. Either basically advertise the same for everybody, or target everybody individually. Two extremes. Like targeted advertisement already kind of works. If you basically advertise the same for everybody, you put it on a big board and say, vote for me, so everybody sees it and there is no targeting. If you are able to send a separate email or mail to each person, you basically target everybody as individual. So two extremes. In one case, everybody as a group. In the other case, everybody separate. The problem is, this is ineffective. Just advertise the same advertisement message to everybody. This is expensive. Delivering personalized advertising messages is expensive. So what people do, they say, okay, yeah, everybody is inefficient, but having like 1,000 people individually is expensive, so I will just try to segment those into two groups. So, males and females, for instance. And I'll target these two groups separately if they behave statistically different. If not, I still target them the same way. Again, that's a kind of the middle ground for the marketing, between advertise the same to everyone and personalized advertising. Even so, we are coming to the personalized targeting. On Facebook, on other social media, you can try to target everybody separately, but still, it's still not really possible even on Facebook. Well, what we do, we basically allow you to specify these groups by demographics, by gender, by geography, and so on. But for that, if you want to do this, it makes sense to understand whether these groups behave differently or behave the same. Everybody with me so far? Again, all marketing is pretty much based on that. In simple terms, there are a lot of details. Now, our goal is to do this hypothesis testing. And this is called something that is, in this case, is called independent sample t-test. Because what we know, we're comparing the averages, the means, males and females. So we know that the distribution is normal. As a result, we use the t-test, and t-distribution is approximately the same as the normal distribution. And what we do, we'll look at the picture, but we compute the probability values that tell us whether we will interpret those in the plot at the next slide. But what it tells us, so if the p-value is less than 5%, the difference is statistically significant. If the p-value is greater than 5%, the difference is not statistically significant. So in this case, what happens? Debt to income ratio, the p-value is 0.75, which is much bigger than 0.5, 0.05. So this is not statistically significant. So what it means that debt to income ratio for the males and females are not statistically different. We shouldn't differentiate these two groups if we look at the debt to income ratio. For amount spent on the primary credit card last month, the p-value is 0, which is of course much smaller than 0.05. So this difference is statistically significant. So what it means, in general population, men are spending more on their primary credit card than females in population, and we should act on that information. We should treat these two groups differently if our goal is to promote and sell credit cards. That's all what hypothesis testing means. How, whether these two groups behave the same or differently based on the target that we have, debt to income ratio, amount spent on the primary credit card, and so on. It's the same, and now let's look at this in terms of the same plot. So hypothesis testing plotted. Somehow this is always a difficult diagram, even so it's still the same normal distribution as we know it. So what we are plotting here? So in hypothesis testing, we have the null hypothesis and turning hypothesis. Our null hypothesis means of the two groups are not different. Our turning hypothesis means of the two groups are different. So if you write it down, in this way, null hypothesis means for the females is equal to the means for males of amount spent on the primary credit card. And the turning hypothesis, those are not the same. Even you may have one hypothesis greater or equal and the turning hypothesis less or equal. You may have variations of that, but this is the ballpark. Now, what this plot is about. So this is a plot of a difference between the means for males and the mean for females. Essentially, we're plotting mu minus mu 0. So that's why 0 is here. One minus the other, the average, if the hypothesis is true, should be 0. Yeah? Now, what happens? So if this difference between mu minus mu 0 is in this interval, we are not rejecting the null hypothesis. If outside, if in this interval or in this interval, we are rejecting the null hypothesis. So what it means that if we get a number p-value in this range or p-value in that range, so it means that the means are not different, the difference between the group is significant. Now let's look at the numbers there. So what we know that this number is 1.96 plus minus 2 standard deviations. In this case 196 to get exactly 95% in this range, because if you get 2 it's going to be 95.5 or something like that. That's why it's not really plus minus 2 standard deviations, plus minus 1.96 standard deviations to get precisely 95% confidence interval. So their numbers here would be, okay, so what we got? So we got the p-values are this, and the t-values are, okay, so in this case the t-value which is on the horizontal scale is minus 0.03, and here is the t-value is 4.7. Minus 0.03 is what? Somewhere here.
How do we get t? It's a mean divided by standard deviation.
Yeah, it's that formula. So it's mean minus divided by standard deviation. Yeah. So it's pretty much the same as that value. So we may try to actually compute it from here. We need all the observations, so you just do it in Excel, and you can verify that you get the same numbers for this data set by doing it manually, by summing up across all the observations.
9.92 divided by 6.37. That would be more than 1.
No. So you need to do it based on the observations, not just the mean. So you have whatever, you have to sum up this. Or 2,000 whatever cases. But yeah, it's always good. So you have the column of numbers, and you just do it in Python for the notebook that we had and compare that you get the same numbers. Good exercise, and after that we verify tomorrow that we are getting. It's always good to verify everything. So that the numbers that we are getting are the same as when you do it manually, implementing that formula for the t-values from Wikipedia or from the book. So t-value is for the depth information minus 0.03, which is, so this is 0 minus 0.3 somewhere here, yeah? What that tells us, so when we look at this area, this going to this is approximately 75%, and this is our p-value. Everybody with me? So this p-value is 75%. This is the area to the left, to the right, sorry, of minus 0.03. So minus 0.3 is somewhere here, so this area would be around 75%. That's for the depth to income ratio, and because it's here, we are not rejecting the null hypothesis, so means are really the same for the depth to income ratio. For the amount spent on the primary credit card, the t-value is 4.7, p-value should be 0. 4.7, so here's 196, 4.7 is somewhere here, so the area to the right of it is 0. Wow, or over 0. Yeah? So we of course rejected the null hypothesis that 2 means are equal, and you should treat males and females when we talk about the amount spent on the primary credit card different. So that's how it works for this graph. What remains to check how we computed these t-values from the data that we have. Well, it's time for the break, yes? Yeah. Okay, so as it's a difficult topic, should we stop here to digest the hypothesis testing?
Sure, let's make a break.
Let's make a break. This is tough when you think about it, but this is all the same concept. So we know that we are interested in the means, and the means are normally distributed. One normally distributed variable minus the other normally distributed variable give us a normal distribution still. That's why this is a normal distribution plot. And after that, we just look at the t-values from which we compute the p-values. So because given the t-value, the area on the right from the t-value is the p-value, and we either reject if it's here, or we do not reject the null hypothesis if it's in the middle. Again, it takes time to do with this, and probably some number crunching in Python to do the comparison and make sure that the numbers that are reported in Python, when you compute those manually, the t-values are the same. To convince yourself that everything that we are doing is correct. Okay, I know that's getting hard. That's why we try to get to understand everything that we are talking about, to supplement your statistics course. Nothing that's basically more than that. Normal distribution, because we are talking about the means. And after that, just looking at the ranges and comparing the areas or comparing the p-values. Tough. So let's, I guess, yeah, after that we'll look at the Jupyter notebook and look at the categorical data. So we need more coffee, looks like. But you still need to wrap up things in Toronto, you will not be able to live for a long term. Yeah. Is it 3 or 5 years?
It's 3 or 4. 5 is unusual.
So Roman just stayed for 5 years because of
The elections were happening in both countries.
yeah, I see. Today is going to be tough. We have one additional lecture which was shifted from tomorrow. Because tomorrow is a graduation ceremony at KSC, so we just moved last lecture from tomorrow to today. Tomorrow we are finishing at 17:20, but today we are finishing at 8. Almost.
Graduation ceremony, this is you take part of this? Or
Yeah, we have the previous cohort of MBA students graduating tomorrow.
Okay, so officially they will be released tomorrow.
Yeah, that's official KSC graduation ceremony at Mistetsky Arsenal. Yeah, Katerina is graduating from the economics program as well. Well, next year you will have the same for you.
У вас будет черная мантия с такой штукой? Серьезно?
Да.
Ничего себе, кто
Уже
слушает?
второй выпускной. Один украинский, получается, с обычными дипломами.
А где вы берете такую штуку?
Их нам просто дают.
Школа дает?
Да.
Ну, кстати, дают все университеты.
Я на свой выпускной, который вот был недавно, подбросила для фотографии шляпку эту, и она пропала, получается, она за полотно упала, и никто не мог ее достать. Вот. И первую шляпку, короче, она мне пропала сразу же.
Ай-яй-яй, а диплом уже дали или это было?
За это не
После
дали.
этого, да.
Вечные студенты, это все.
Как вот это была карикатура, правда, що у нас в анекдоті, що випускники філологічних факультетів можуть кричати вільна каса на 8 різних мовах, так це ж прийшло зі Штатів. Тобто у них така карикатура з 50-х років, коли вони во время градюшниці вони підбрасують цю шапку мантію, а назад падає кепка Макдональдс. Типа, і всі ржуть. А вообще-то про мантії це взагалі прикольна історія. На самом деле оці всі ж професори, вони ж сидять в різних мантіях. І це мантія з того університету, ти робив PhD. Тобто кожен університет, там у Кембриджа своя, зі своїми там кольорами, логотипами. Що своя, як більшість професорів, хто хоче, тобто вони купують собі цю мантію, зі свого університету вони закінчували докторантуру, і потім сидять на цих церемоніях, всі в цій мантії. Я так собі ніколи не купив. Зі свого канадського університету, де я робив PhD. А це було прикольно, в кольорах там все. Але, во-первых, жаба дали платити $1000 за мантію, а во-вторых, якось ніколи особливо...
Понти коштують гроші.
Понти коштують. Тут я повністю згоден. That's exactly the case. But there are simpler cases. We were just discussing that these gowns that people wear during the graduation ceremonies. So for professors, it's from the university they did your PhD. So that's why we have different colors. Somebody is from Stanford, somebody is from Cambridge, whatever, somebody is from UFT, and that's why all professors are in different gowns, in different colors. But typically for students, you basically have the same gown, but it's a different treatment. So it's another interesting ceremony, at least in Canada, there is a British university system. So when you finish your bachelor, so during the graduation ceremony, when you get a diploma, there is a chancellor, Chancellor Universitetu of the university, and if you are undergrad, you come to the throne that person is sitting, the chancellor is sitting, and you need one of your knees. So you basically стоїть на одному колені, становитесь, Він пожимає руку і він сидить. So he is sitting and he is shaking your hand. If you are reading from masters, he is still sitting but you are not kneeling on the knee, shake your hand. So when you're going from PhD, that person is standing and shaking your hand. So it's like the same level of academic degree at that point. That's very many of those interesting traditions.
So nice.
Yeah, I don't know what KSC has implemented, so I have never been to the KSC ceremony, but yeah, some of those are fun. And Canada is pretty much more closer to the British than in the US. You all have all these Olinkas, so the Scottish traditions, they're playing on the pipes and things like that. Yeah, typically again, so when for the graduate degrees, typically if you have a supervisor who is spending the same money, he or she is put on the gown. When you enter the stage, when you have to take a shon, the hood, not the gown, when you enter the stage, and other small things. Pretty interesting, okay.
And Latin.
So, you can start this. It's okay, we just, as always, it's much easier to talk about something not related to the course. That's our Ukrainian tradition. So this for next is
Таке відчуття, що у вас зовсім інша презентація, ніж ту, яку ви поклали на Moodle.
really.
Є.
Це інше. Basic statistics.
Ну, саме, наприклад, той початок, де там були схили і так далі, там зовсім інші визнаки.
That's what happens when you updating the slides, so we'll need to check what is. So here is different. Let's check. Shall I log me out? Oh, yeah, the internet is not
Ні, no internet, yeah.
reliable here. As expected. Basic statistics. I have it. Okay, let me check it. So what I posted. So probably something may have been different. Blah 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 blah. There may be some slight difference here, so not slight. Please notice some. Oh, yeah, I mean, no, of course, in the number of the slides, probably there is a difference because I probably deleted some slides with videos and stuff like that. So that's why numbering may not coincide. Yeah, that's true.
But not only numbers and diagrams, some different diagrams and stuff.
Yeah, I'll check and update. So
Okay.
that's. Okay, so let's now, just to switch the gears, let's look at the Python code for the same analysis that we did on the slides. So, we are going to do the same things here using this. So we have in this data set of these 5,000 customers, and we have different columns in the data set, such as gender, age, debt to income ratio, the primary card used by that person, Visa, MasterCard, and a bunch of other things. So in this analysis, we'll mostly use the two columns of data. We'll use this debt to income ratio, and we'll use the amount spent on the credit card, this card spent. But you can also play with other columns in the data set. So we load the data set using pandas data frame from the CSV file. Nothing new here. After that, we first, as always, we start with data exploration. So typically, we may use a describe command in pandas, which computes the number of observations, the means, and the deviation minimum, all the quantiles and the maximum. So that's automatically done for each column in the data set. And what you can immediately see, that's another important concept for the commute time. There is some missing data. You see everywhere is 5,000 observations. Over here is 4,098. So there is two missing data points for the commute time. We didn't use commute time in our analysis, but if you have missing data, not the numbers, so it may screw some of your statistical algorithms, and you may need to deal with this using data cleaning. So either you just remove those two observations from data, or you need to impute the numbers for the commute time if you're going to use commute time in your analysis. Again, something to pay attention, and this is a very useful describe command that immediately tells you how many data points you have. 5,000 observations, so we should have 5,000 data points. If it's less, there is some missing data. And we have to look at it and do it. So this is another part of working this data. Dealing with missing data, we'll just touch base about it in this course, but there are a whole range of algorithms how you work with missing data. You can also create the new columns easily in pandas. So if you need that for data analysis, here is an example. So for instance, if you want to create the column with high income and low income, 0 ones, and high income is more than 30,000, low income is less than 30,000, what you can do, you can use this function that basically creates a new column income category. So it takes the annual income, and if it's greater than 30,000, it returns 1, otherwise it returns 0, and it populates the new column. So you can create new columns in the data if you need those based on the other columns. Essentially, that's something what is in machine learning called feature engineering. After that, we select just the 4 columns, and we are going to do the plots. So we can first we look at this missing data. For this commute time, we had 2 missing data points, and if we look at those, so those are 2 observations with missing points, and we can try to impute the commute time, or we can try to ignore these 2 rows in the data. After that, we just, with the histogram, we can plot all the 4 columns of data, and that's our standard bar plot for the histogram. And as we see for some of the columns, the distribution looks like approximately like symmetric and maybe normal, like commute time or card items, but for the other items it doesn't look like normal, it has effect there, as for the depth to income ratio. We can plot those data points separately, the columns separately instead of plotting together. And next, as we did before, we can compute the confidence intervals using the SciPy package. It's stats functionality, and this is pretty much our functions to compute the means and standard deviations, what we did on the slides. And after that, we can use this stats normal interval and compute the 95% confidence interval, and we get the same interval as it was on the slides, from 9.78 to 10.14% for the depth to income ratio. And that's what we can print, that's a confidence interval. We can do statistical tests in Python. Again, we have this gender column, males, females, and we can now do the same hypothesis testing as we did before. So we compute our means for current amount spent on the primary credit card and for the debt to income ratio. And we can do our t-test, our hypothesis, which returns the t-value and the p-value for the this is for the amount spent on the primary credit card. P-value is minus 4.74 and the p-value is almost 0. So in this case, we know that the means are statistically different. And then we do the same for the debt to income ratio. Our t-value is 0.3 and the p-value is 0.75. So in this case, we know that the numbers are not statistically different.
May I ask a question? There are in principle 2 tests, p-test and t-test, yeah? P-test is used.
No, it's the same.
But
so p-values and t-values. So the test is called t-test.
Yes.
Yeah.
P-values, t-values, and for p-values, when we know the standard deviation of the population, yeah.
Yeah, and you can compute t-values and p-values.
And the question, when it's practically we know this standard deviation of population.
Basically, what you do, you make pretty much an assumption that your standard deviation of the sample is approximately equal to the standard deviation of the population.
So it's mostly really the assumption.
Yeah.
And in fact, I think t-test is used. Yes, that's why, because
otherwise, if you basically need more complicated assumptions, you need to go to more complex tests such as ANOVA, analysis of variance, where their standard deviations may be different, and you can incorporate that into the test.
I just was curious what's really the real case, yeah, when we know standard deviation of population.
Again, if you see big differences in the standard deviations of the two groups that you're comparing, or if you expect that the standard deviation of the sample may be completely different from the standard deviation of the test, you probably have some issues with your data. So your data is probably not random, not independent. In that case, you need to really do some investigation before you do the hypothesis testing. So in practice, if you collect the data, if your sample is random and representative, the standard deviation of the population should be close to the standard deviation of the sample, and you shouldn't do any corrections for that. Otherwise, if you expect this to be hugely different, there is probably something miscollecting your sample. It's probably not random, actually. And that explains the difference. And after you try to correct for that and not really adjust for the standard deviation during the hypothesis test, you first try to correct your sample, how to collect the sample which is really random, which removes that issue. But if you have hugely different standard deviation of the two groups that you're comparing, you move to another test which is called the ANOVA analysis of variance, which is adjusting for two different standard deviations of the two groups. In our case, because standard deviation for males and females are approximately the same, you are fine with the t-test. Again, every test is allowing you to compare something to something. So typically we compare groups, and for the groups typically we compare means. But you may want to compare medians for the two groups. You may want to compare modes. You may want to compare standard deviations. You may want to compare ratios. This is not typical, but if you want to do that, you go to another test. You read what other tests are available to compare, instead of means, to compare medians, for instance, of the two groups. And so on. So all these tests are really dealing with different distributional assumptions and different numbers that you want to compare. So again, typically you want to compare the means. But if you really are analyzing whatever income and you want to compare the medians, you need to look up which test compares the medians instead of means, because the distribution of the medians is no longer normal as the distribution of means. There is no central limit theory for the medians, so you need to find another test to do this hypothesis testing. That's why people typically don't go beyond comparing the means. It's just getting too complex. And you'll see that for categorical data, there is another test. Now we are dealing with
It's just square test.
yeah, and for the t-values and p-values, you can, as soon as you compute the t-value, p-value is computed automatically. So as we said, as soon as you know the t-value and you have the formula for that, the p-value is just the area of the distribution to the right of the t-value. So in our case, the t-value was minus 0.3, which is somewhere here, minus 0.0, minus 0.3. So this area is the p-value, which was 0.75. In the second case, the t-value was something like 4.7. So the area to the right of it is 2 to the power 10 to minus 6. So almost 0. So that's all. So you can just get that from the table, because t-values directly project to the p-value, so there is no difference. You can look at the t-values in hypothesis testing, or people just prefer to work with p-values because those tell you there is a threshold of 0.5%. Well, the threshold because of the 95% confidence interval, the p-value of 0.5% tells you whether you reject or accept the hypothesis. That just corresponds, because this is 2.5%, is 2.5%, so we have this 5% p-value threshold for comparison. Even so, nobody really prevents you from changing the threshold to 0.01. In that case, you just extend this and leave here 0.5 and 0.5%. So again, it's your choice of the confidence interval. Typical choice is 95%, but nobody tells that you shouldn't use 99% confidence interval. In that case, your threshold moves from 5% to 1% of the p-value threshold. And this is not, so this threshold that we used is not written in stone. It just corresponds to, if you decide to use 5%, it's 95% confidence. If you decide to use 1%, it's 99% confidence. You use 10%, it's 98% confidence. This is your decision, which threshold to use during your hypothesis test. The standard practice is 95% confidence interval, so the threshold is 5%. But nothing is written in stone in statistics. It's your interpretation of the data. Yeah, nobody tells you what's that. The thing is, when you work with data, a lot of things that you need to do is the interpretation of the results. Because all these tests can only tell you what's going on, but there is always uncertainty. There is always uncertainty in this. We are modeling something that is uncertain. All those things are random variables. So you make some assumptions, you do your statistics, and after that you interpret your result. But nobody basically tells you that use this 5%. Up to you. That's why decisions that we are making are based on data, but after that it's also based on interpretation and thresholds that you put into your model. Okay, any other questions about this diagram? So what I suggest you to do in that Python code that I just showed, go and compute the t-values manually from the formulas using the same data, and make sure that those are the same as reported in the Jupyter notebook. So make sure that this t-value that you get from this function, from the t-test, is, and then you compute it manually, is the same. That's your sanity check. Using that formula that Tatiana provided to you. So you have the data, you have these 5,000 observations, so just add one line of that formula that does the same computations, make sure that t-value that you are getting is also 0.3. That's a key for understanding. So you can also do the other plots, you can plot this. So this is a whisker plot, which is standard for plotting the percentiles. So here is the median, here is 75th percentile, 25th percentile, this is the minimum, and this is typically the maximum or the 99th percentile. So this is really allows you to visualize the percentiles for two groups, for the males and females. And if we overlay this with data, you see that exactly 50% of your data are between 25th and 75 percentile, and there is some data, 25% of your data is underneath 25th percentile, and so on and so forth. So this is all the plots. And you may look at some other interesting relationships in your data. So that's one example of what else you can get. So this is income plotted versus the age, and what you may expect that, yeah, your income should grow till the retirement after drop. But what it shows that the income grows till approximately 55, 6 years, and after start dropping. So income actually start dropping before the retirement and not at the retirement. So there are some interesting patterns in the data that you may act on and incorporate into your analysis. So plot, visualize, look at some interesting patterns and try to convert those into decisions. Yeah. Look at your data, visualize your data, and see what's there. Do exploratory analysis before doing anything more complex. There is also a Jupyter notebook of overview of different distributions. Feel free to look at that yourself. So which distributions are used when and what those means. So this is a uniform distribution. You can plot it, what it means. So there are also normal distribution, that's what it means. Here is different plots, exponential distributions, geometric distribution, Poisson distributions used for different cases. Useful to get familiar with different distributions and know what we can model with those. We get back to that to some extent when we talk about Monte Carlo simulations, where people develop the best practices, which processes can be used by modeled by which distributions. Like arrival times by exponential distribution, the wait time typically by normal distribution, and so on. So people have worked on that and figured out which processes that we found in nature can be best described by which distributions. Any other questions? So let's finish with statistics. We have probably spent enough time. Categorical data, very briefly. Examples of categorical data: gender, age groups, product categories, and as we know, to differentiate between quantitative numerical data from one side and categorical data from the other side, we should ask the question, does it make sense to compute the mean? If the answer is yes, this is quantitative or numerical data. If the answer is no, this is categorical data. So for instance, does it make sense to compute the mean of the temperature? Yes, that's a quantitative numerical data. Does it make sense to compute the average gender? The answer is no, this is categorical data. So that's a rule of thumb. In our example, let's look at only one example of the categorical data, and this is what we have here. So we have the users of iOS versus Android, so two operating systems or two devices, so two categories here, and here the age groups, so 1, 2, 3, 4, 5, 6 categories for the age groups. And we have the number of people in each of these buckets, so the number of Android users between age 18 and 22 are 93 people. So first what we do, we convert those absolute numbers into percentages, such that it sums up to 100% in each row. So this is now the percentage of users of the Android devices in this age group versus the iOS devices. And we can always plot, so this is plotted also by operating system Android, iOS, colors represent different age groups. And one observation we can make, looks like younger people prefer iOS devices, iPhones, so 16% versus 14% and 33% versus 30%, while for the older people, they prefer the Android devices. And this is the hypothesis that we would like to test for categorical data. Is it really true that people who are younger than 32 years prefer Android? Is this difference statistically significant? And the people who are older than 32 years prefer iOS, Android if they're older than 32 and prefer iOS if they're younger than 32. Again, this is another hypothesis we'll test here for the categorical data. And the decision is, if this difference is statistically significant and you have a younger person who walks into a store, you first propose them to buy an iPhone. And if you have an older person who walks into the store, you first propose them to buy an Android device. Again, that's how we can use the segmentation to two groups if the difference is statistically significant. For this, you can also compute the margin of errors and stuff like that if you want. And after that, you can do a statistical testing. And in this case, as I said, what we'll be testing that people who are below this age prefer iOS, and people who are above this age prefer Android. That's what our data shows us, but we just want to know if this difference is statistically significant. For this, there is another test, because we're using categorical data. It's called chi-square test. More difficult to visualize it, so I'm not going to do that. But what you can do, you can also compute something similar to the p-values. It's called as asymptotic p-values or something like that. And it's going to be 0.33. So 3.3%. So now, with the threshold of 5%, is this difference statistically significant or not?
Yes.
Yes, it's below 5%. So this difference is statistically significant, even so it's pretty close to 5% threshold. But still, we interpret that, yes, this difference is statistically significant, so we should treat these two groups differently. And really, we should, if a young person works into the store, we should first propose them to buy an iOS device, iPhone, and if an older person works into the store, we should first propose them to buy an Android device. So we should treat these two groups differently.
Reject null hypothesis.
Yeah, you are rejecting null hypothesis. So which, in other terms, the two groups behave statistically differently. So distributions, as I said, make sense to get familiar with distributions. We don't need to remember much, just need to approximately know how those look like. For the major one, normal one, uniform is popular, exponential is popular. People use binomial, Poisson, geometric sometimes. Again, it comes with practice. You don't need really to remember much, but these are the three main types of the distribution. So for the normal distribution called Gaussian, you know that it's symmetric, and you know that mode, median, and mean coincide. And for the positively skewed distribution, such as log normal, so here is the mode, the most popular value, here is the median, here is the mean, and this is for the exponential. All these formulas nobody remembers, so different distributions from statistical textbooks. So this is the PDF, probability density function, that is really the distribution plot. So this is this function that we plot. For normal distribution, for instance, this looks like this. That's an exponential function, this bell curve. Here is how to compute the mean, how to compute the variance, how to compute moments, how to compute CDF, cumulative distribution function. Again, we all have this in the code in Python, so R don't need to remember this, but somehow people put it in the statistical textbooks in many cases. And the last point that I would like to make for this part is that when we just start working with the data, we started looking at distributions, but the output of our models can be distributions as well. So our variable that we are trying to model, our random variable, in this case, average temperature increase, when the amount of the CO2 in the atmosphere doubles compared to the pre-industrial level, that can be the result, distribution can be the result of our model. That's another thing we want to remember. We may look at distributions of our initial data, and the result of our modeling can be a distribution as well, when we are trying to model a random variable. And in that case, the interpretation, how we get it, so we'll talk about that during the Monte Carlo simulations lecture, but the interpretation of the results will be the same as we just did in statistics. So you plot the distribution, you look at the one-number summaries, you look at the minimum, maximum, mean, median, standard deviation, percentiles, and so on. And you also look at what happens in the worst cases, in the 5% or in 1% or in 10% of the worst cases. And you are especially trying to figure out how to deal with the worst cases. In this case, as I said, the 95th percentile is 4.7. And basically what it tells you in the 5% of the worst cases, this area is 5%, the temperature will increase by 4.7 degrees or more. And this is a danger zone. That's a huge increase. So what you will try to figure out next, after having this model, which factor caused this huge increase, and how you can potentially deal with those factors. So what is really causing these extreme cases, these black swan events? That's really important to figure out, because this is a danger zone. Probably, I feel here 1-2 degree temperature increase is okay, but it's not okay what happens in the worst 5% cases. Okay, central limit theorem. What this central limit theorem tells, and basically what it tells, the mean of the large number of random samples from any distribution will be normally distributed. So that's the main conclusion of the central limit theorem. So if you write it this way, what it says, if you sum up random numbers from any distribution, so x1, x2 and so on come from the same distribution, but it can be any distribution, any strange distribution. Those are going to be normally distributed with this mean, with this standard deviation. And when we divide both sides of the equation by n, so to get the mean, so all this sum divided by n, so that's a mean. So this is getting n by n disappears, we just get the mu. Here we need to divide by n squared, we have this. So what it tells us that the mean is going to be normally distributed around the population mean and around the standard deviation. That's all. This is the central limit theorem. So it doesn't matter from where these random variables are coming from. The random variable x bar, the mean, will be normally distributed. How this is, how we can show this? Okay, if you're going to be drawing numbers from any distribution, and I'll probably start here. There is an interesting online tool there where you can go and convince yourself that it works. You can design your own distribution, anything that you want, any strange distribution, how it looks like. And after that, what it does, it just samples from that distribution, compute the mean, in this case the mean of 2 numbers, in this case the mean of 25 numbers drawn from the distribution, repeats that many times and plot the distribution of the means. Everybody with me, what's going on? You sample from any distribution. It can be log normal, can be this strange distribution, doesn't have a shape, can be geometric, can be any sort of distribution. You take random number 1, random number 2, compute their mean, plot it here. Take another 2 random numbers from here, compute the mean, plot it here. Repeat that many, many times, you get this. You see, even this averaging 2 numbers drawn from distribution, it already looks like normal. When you average more, in this case 25 numbers, it looks completely like normal. And of course, the more number you average, the smaller is the standard deviation of the normal distribution. So here is the standard deviation is this, here it's much smaller. And that's what you see here. So we repeated this exercise 100,000 times, get into numbers, compute the average plot, repeat 100,000 times, you get this. And the standard deviation of this is 4.65. After you average 25 numbers, the standard deviation is 1.32. So this is completely normal distribution. But this is already approximately normal even when you average 2 numbers. So here you can see it another way. So here our initial distribution was like uniform, approximately. It doesn't matter from which distribution you draw. You average 4 numbers, you get this. You average 7 numbers, you get this. You average 10 numbers, you get this. And when the number n increases, the number of the samples that you average, distribution becomes more and more normal, and the spread of the distribution decreases, the standard deviation decreases. So that's all what central limit theorem is telling us. It doesn't matter what distribution your data is. It can be anything. It can be not a distribution that has any analytical form. It can be anything. So it doesn't really matter how your data is distributed. It can be anything. As soon as you are interested to make conclusions about the means, about the averages, how average person votes, or how the person votes on average, whatever we call it, how average buy and title, average behavior under the promotion of the customers. You can use this central limit theorem because you know that the distribution which you will use for hypothesis testing, for instance, is going to be normal. If you want to compare the means, your distribution used for hypothesis is going to be normal because that's what central limit theorem is telling. Distribution of the averages, doesn't matter where those numbers are coming from any distribution, is going to be normal. Everybody with me on that? That's the underlying property of basically most of the statistics and hypothesis testing. Nice property that is really undervalued, and this is probably maybe even more, the most important reason why normal distribution is so important, because of the central limit theorem. Distribution of the averages is always normal. Okay, now how we can use this, for instance, for the same election polling. So what it tells us as basically that's what we write in the central limit theorem in terms of the formula. So the central distribution of the mean is roughly the formula normal distribution, or for the normal distribution we know that 95% of time individual sample mean should be within plus minus 2 standard deviations from the population mean. So, and that's what it tells us. So this is our sample mean, which is plus minus 2 standard deviations from the population mean, plus minus 1.96. And the probability of that is 95%. That's again, under the normal distribution to be, for the sample mean to be plus minus 2 standard deviations from the population mean mu. So this is sample mean, x bar is population mean. This is 1.96 of the standard deviation. So this probability of that is 95%. Again, this all holds for normal distribution. We know that. That's what we can write down for normal distribution under central limit theorem. And yeah, this plus minus 1.96 standard deviation, that area is 95%. Now, how we can interpret it as a margin of error and stuff like that. So yeah, we also have the sample variance and the population variance. So sample variance and population variance divided by n, or we can take the square root of that. So now we can replace this sample standard deviation by the population standard deviation divided by the square root of n. N is the number of observations in this formula. Nothing else changes. And after that we can rearrange. We can move x bar here and mu inside. So how this is interpreted, so if we are really interested in the population mean, so the population mean is plus minus 2 standard deviation from the sample mean. We know sample mean, we know variance, so we know this number, and this is exactly the number which is called the margin of error. So this actually is the formula for the confidence interval. So confidence interval, so what we said, the population mean mu is the sample mean x bar plus minus 1.96 standard deviation by n, plus minus the margin of error. So here is the plus margin of error, here is the minus of error. So this gives us the confidence interval, which holds with the probability of 95%. Oh, which holds with 95% confidence, sorry. Okay, and we know this. So this equality is because of a normal distribution, because of the central limit theorem. So this is margin of error. Now let's put this to our election polling. Let's compute how many people we need to poll if we want to, or let's compute the margin of error if we poll 1,000 people. So let's say that we want to poll for the election, we poll 1,000 people and 550 people of them responded they vote for the candidate A. And let's assume that these 1,000 people that's a sample which is random and representative. So how confident then we are going to be that the average person, on average, the person will cast their vote for the candidate A? That's the question. Now, when we are basically have a process where the voter can choose candidate A versus candidate B, this is a binomial distribution. But again, underlying distribution can be anything. In this case, it happens to be binomial. So for the binomial distribution, so what we have the form, all what we need for the binomial distribution, we need the formula for the standard deviation of the binomial distribution, which happens to be square root of p multiplied by y minus p, and p is 0.55. 51% vote for candidate B. As a result, 45% vote for candidate B. So 0.55 multiplied by 0.45 square root, that's a formula for the standard deviation for the binomial distribution. When you choose among two alternatives, that's a binomial distribution, another thing. Now, what we also have, we have this formula for the margin of error, and that's what we want to compute. So first we take the population standard deviation for the binomial distribution, divided by the square root of n is the number of observations, 1,000 people. So 0.55 over 0.95 square root divided by the square root of 1,000. We get this number, and now to get the margin of error, we need to multiply by 1.96. 1.96 multiplied by this number, we get 3%. So margin of error, when we poll 1,000 people, is 3.1%. That's where we get the margin of error. Why this holds? Because central limit theorem. Doesn't matter from which distribution we sample, in this case from binomial distribution. As soon as we need to work with averages, how people vote on average, we can apply central limit theorem. And for central limit theorem, this is the margin of error that we get with the 95% confidence.
Why do you take 0.65 and 45?
That's because in our sample, there 55% people vote for candidate A and 45% for candidate B. But it doesn't matter. So this is
But we can take 51% versus 45.
well, that's what you get from the data. When you ask the people whom we are going to vote for, 550 people vote for candidate. If you got another number, substitute another number. So here is P is the number of percent of people who vote for candidate A, 1 minus P is number of people who vote for candidate B. Can be any numbers, doesn't matter. The results are not going to change dramatically.
Yeah.
It's going to be still around 3%. Plus minus, slightly lower, slightly bigger than 3%. That's why nobody really cares how many people vote for one or the other. The margin of error will not change by that much. So that's why everybody tells you 4,000 people, you get margin of error 3%. In this case, it happens to be 3.1%. If you choose these numbers differently, maybe 2.9%, but still close to 3%. Yeah, that's all. That's how election-based polling is done, or any other customer-based polling for in marketing, in sales, in promotion design. That's what it is. But this margin of error is only true if our sample of 1,000 people is random and representative. If that is not the case, as it was in the last election, this number will be much bigger. And that's why our conclusions may not be correct. So our conclusions are based on the sample being random and representative. In that case, margin of error of plus minus 3%. If you screwed up this and your sample is dependent, this is maybe much larger.
But how did
95% of the time.
they make this big mistake in the US? Because they invest many money, and so.
Well, that's why we discussed all those reasons why it is so. When you call to the phones, you cannot call. Why
didn't they understand it? Yeah, because okay.
Before the election, nobody cared because everybody was thinking Clinton will win, and their poll results supported that. So it's a people's bias. So you expect to see what you expect, and that was short. But at the end,
But it's also that 95% confidence means that the opposite thing happening is not that rare. 95% just means 19 times out of 20. So it means like 1 in every 20 times the other thing will happen, even when you do nothing wrong.
That's true. But even if you
95% is not that really that confident in.
That's true. But you see, if you want to get a margin of error of 1%, no. If you want to change the confidence, you just need to poll more people.
A lot more.
And that's much more. So pretty much, if you want to move from 95 to 99, I think you will need, instead of 1,000, you need 10,000. 10 times more expensive. Nobody's going to do that. Just 10 times more expensive to poll. And that's all. You cannot afford polling more people, because now this 1,000 you need to do in every state in the United States. In every state you need to poll 1,000 people. But multiplied by 50 states, 50,000 people. Already too expensive. Of course, you disregard some small states and blah blah blah, and make some other approximations, but That's what it is. Too expensive to call. When you call on the landline phones, you poll all people. When you call to the mobile phones, you need to get the database of mobile phones. There is no yellow pages for the mobile phones in the United States. All these reasons that it's just getting too expensive to make sure that your sample is randomly presented. And it was all okay if the difference is huge. So if 55% versus 45%, that's okay. Plus minus 10% even maybe okay. But if the difference is, like 52 versus 48 or something like that, that's it. You need to be precise. So that's why in the previous elections of Obama, so the difference was bigger and nobody really cared about this error. So the difference in polls, Obama was leading by much more. So if the margin of error was 10%, so 3% is still okay.
But also, in aggregate, the polling wasn't that wrong. It was just in the segmentation that it got wrong.
That's true. But things got worse with Trump because that's a bit of a mindset change. So there's some protest electorate basically there are so many complications for this election because of Trump. And we're not even talking about Russiagate and the influence of Russian hacking and misspread of disinformation, things like that. That also should be factored in there. But it's difficult. So the thing is to make things precise, just too expensive. Probably it's better to abandon it and say, well, you cannot just predict elections from polling.
It was red swan.
Yeah, exactly. So that's what I put here on the slide. So because of these rates, we have the red swan because of the Republican Party is red.
Yeah, orange.
Red swan instead of blue swan. Well, that's why now, it's interesting impeachment story and Russiagate, Ukrainegate, and things like that.
But did they have in the US exit poll? Do they have also exit poll procedure in the US?
I think no.
They don't.
Yeah, no, they do. They do.
They do?
It's not in Canada, but in America they do have exit
Oh,
polls.
they have exit
Yeah, they're illegal in Canada.
And exit polls didn't show that.
No, I think exit polls they did show, which is why they called it so early. Yeah.
But in Canada, we know the results a couple of hours after
Yeah.
the end, so that's why who cares about the exit poll? So pretty much their polling, their election ends at 9 p.m. I guess
9 p.m.
in the evening, and after that, by 11 or by midnight, you pretty much know 99% of the selected MPs. There are still probably a couple of constituencies where it's not clear, but you know what happened already 3 hours after.
Yeah.
So that's why exit polls do not make much sense, because you know the results in a couple of hours. And yeah, this is all what I also explain in this sense about uncertainty and what happened with the election. So let's not stop there. What is margin of error, variance, standard deviation. You also, if you work with more than one random variable, you need to look at the correlations and covariances, because your data may be correlated. You need to take that into account in terms of statistics. So you need to understand what are the covariances, what are the correlations between two random variables, and if you have more than two, you have the covariance matrices, correlation matrices, things like that. And another last about election statistics. So this is another thing how you can use this central limit theorem for detecting fraud in the election. So these are the election results. So here is the turnout of the voters. It's called turnout in Ukrainian. How many people show up and vote? Yes. Here you have the turnout, and here you have the number of polling stations where they computed the votes. So this also should look, according to the CLT, as approximate normal distribution. Of course, it has a bit of a fat tail at that. It's okay, but it should look like this. That's what central limit theorem is telling us. And these are the election results for Canada, US, Ukraine, Poland, Bulgaria, and everywhere it looks like normal, approximately. And now we have the election results in Russia. And you see what happens here. Russia violates statistical laws. So according to Russian elections, central limit theorem is no longer valid. And what happens here?
Jumps 75%.
Of course, people like to. What we do in Russia? We don't care about fraud at the time. When the process believe me, we just change the numbers as the polling results. So the chair of the commission just put, okay, I think 70% should vote for Putin. I put 70%. That's why we have jumps. They just change the numbers without really putting the new bulletins. So that's why you have and people like to put round numbers. 80% voted for Putin. So that's why we have spikes at 80%. So this is really clear. You can easily detect. So this was the parliamentary election and the presidential election. So for Irina Russia and for Putin. And yeah, they just put the numbers, 70% or 75 or 80 or like these round numbers for the candidate that we need to put into the results. So when they report this, so when each election commission at each constituency reports this, they just make up the numbers. And nobody even cares about more advanced, fraud. So it's not like it was even under Yanukovych, so they had this Pechenye and like special buses with voters going and voting out of stations. Russia, nobody cares about special buses. You just put the numbers that you want as the chair of the election committee at that polling station. That's all.
Including 100. The number of 100 is kind of amazing.
Exactly. Or some people like to put 100. So that's why you have a spot. And that's how we estimate it. Even if, there is a slight of a fat tail here, which may happen, so it should be normal. So this was for Duma election 2016, Russian parliament, and this is for Единая Россия. So for other parties, they still okay in terms of other parties get approximately central limit here. Единая Россия, wow, and this is at least the difference that this is at least the fraud. So we estimated the fraud this way. So as you see, this is a complete fraud. Whatever you do, so this amount of voting fraud resulted in this Единая Россия party, which is the presidential party in Russia. And this is just the sum of the result of the other parties. You subtract one from the other, we don't even compare it, it's not summing up to one. Who cares? Or you just put the numbers that you like. The same here, this is for some other election. I guess we see all these round numbers. Looks very nice, and it's only look like this for one party. Other parties are approximately as it should be, but Единая Россия, the ruling party is like that. Okay, so that was the review of statistics. So any questions? Very interesting. Even not going beyond statistics, we already do some interesting algorithms, some interesting conclusions based on data science. And statistics is just a very basic type of algorithm. So we didn't even start talking, as I said, about optimization modeling, simulation modeling, machine learning, and stuff like that. Even statistics already give us many, many interesting insights. Questions before we get to the hard part, to the review of mathematics. Okay, the goal is that you understand everything. So if basically the understanding is the key. And that before, how many we have? 20 minutes? Yes, so
We skipped lecture 3, yes?
that was a review of Python. We decided not to do the review of Python because either you know how to program in Python, you'll take a preparatory course, or you'll take online courses, so it doesn't make much sense to spend 1 hour reviewing of the Python syntax. That's why we decided to skip lecture 3. And
do it ourselves on our own time.
Yeah.
Okay.
We can still get back to it. So up to you. You tell me what to do. So what I put for now, that Python lecture is optional. We can always, if you want to have a review of Python programming, we can always get back to that. Tomorrow.
2 hours is not enough. So
We are moving pretty well. We are now at lecture 5, review of mathematics. That's what we'll probably finish today, and tomorrow and the day after we'll go to this more interesting algorithms such as regression, machine learning, optimization, simulation. So it'll spend pretty much 2 days looking at the algorithms, understanding the algorithms. But today is big picture plus review of statistics now of mathematics, linear algebra, metric computations. And it should be at the level of understanding. So at any time you should stop me if you don't understand something. There is also a handout that I prepared that will also take a look at this. What else? Oops. Okay, now let's start using the flip chart. As I said, in data science we work with functions. Everybody remember that? High school stuff. Це ще шкільна програма. So we work with functions. Functions look like this. We should be able, even in the school, plot this function, any function, at least the function of one variable, the function of 2 variables. Of course, plotting the function of 1 and 2 variables, so we can plot this, and we can plot this function of 2 variables, because it's 2 dimensions, x and y, here is 3 dimensions, 1, x, 2, and y. Plotting functions of 1 and 2 variables is difficult, because we need 1 and 3 dimensions, but to see everything, it's enough, these 2. So next, so what we want to understand about functions and why we need those. First, interesting thing, which I actually have on the slides, is the simplest algorithm that will power many other algorithms. I also have the review of what you need to know from mathematics, and we may look at that, but the simplest thing that we may need is solving linear equations. Anybody remember this from school? Can you solve a linear equation if it's one variable? Should be very easy. Can you solve linear equation when there are two variables?
Yes.
Yes, we did it at school, and you probably did it at the preparatory mathematical course. So what we studied in school, if you have the linear system of two equations, two unknowns, x1 and x2, two equations, yeah? Now what you do, you can express one variable through the other, express x2 as this function of x1, and after substitute x2 into this, and you get one equation in x1, and it's now one linear equation, and you express x1, and after x1 is equal to 2, and you substitute x1 here, you get x2 is equal to 5. So that's what we studied in school. In general, we can write down the system of linear equations in the vector and matrix form. In data science, it's very convenient to work with vectors and matrices, just because typically we don't work with two variables or one variable. We may want to work with millions of variables. For instance, in machine learning, we have a million features. Then we have an image, which is 1000 by 1000 pixels. In terms of each pixel the feature, it's automatically million variables in our function. So that's why writing million variables as a scalar doesn't make much sense. So we always would need to do everything in the form of vectors and matrices. And that's what we'll spend time understanding, that it's not that much different from the scalars. So to move to matrices and vectors. So system of linear equations, we can write down in the vector form. So we denote matrix A as a matrix of coefficients, 3, 8, 10, minus 7, 3, 8, 10, minus 7. We denote the vector B as the right-hand side constants, 46 minus 15, that's vector B. And we denote the vector X with two coordinates, x1 and x2, as a vector of unknowns. Yeah, everybody is okay with that? And after that we can write down the system of linear equations in this form. Matrix A multiplied by vector X is equal to B. And you probably still remember how we multiply the vectors and matrices. When you want to multiply A by X, you just... So 3 multiplied by x1 plus A multiplied by x2 as a first. Yeah, remember from school? Yes, no? Let's do it on the board. So this is 3, 8, 10 minus 7 multiplied by x1, x2. Yeah, so this is A multiplied by x. So what we do to do this multiplication, so you do this 3 multiplied by x1 plus A multiplied by x2. Everybody remembers, or 3 multiplied by x1 plus A multiplied by x2. That's the first coordinate of the result, and here we do the same for the second. Just 10 multiplied by x1 minus 7 multiplied by x2. And this is the result. So the resulting is the vector with two coordinates. It's the first coordinate, second coordinate, and that should be equal to B. So equal to B, and that's our system of equations. So D is 46 minus 15. So, and now we are back to the scalar notation. So this is equal to 46, this is equal to 50, minus 50. That's what's written here when we do the multiplication. Now, of course, as we have this general form, and it doesn't matter the dimensionality, axis can be million dimensional, this can be million dimensional. Now we need an algorithm that allows us to solve system of linear equations of any dimensionality. We'll see why we need. So that's the basic stuff. We need to be able to solve linear equations and systems of linear equations. For the more complex algorithms, such as regression uses that underneath, optimization algorithms uses this algorithm underneath. So now, what we can do? First thing that you can do, so we have this. Now you can multiply both left side and right side by A inverse. A to the matrix A to the power minus 1. So what is this? Matrix A inverse multiplied by itself. Yeah, that's identity matrix. So remember, identity matrix is a matrix when we have ones on the main diagonal and zeros everywhere else. Alina, yes?
Yes, sure.
Remember? Because you are too thoughtful. at this moment. So identity multiplied by x, what is that? X. So identity matrix multiplied by x is just x. So this is x equal to A inverse multiplied minus b. So now we have one possible algorithm to solve system of linear equations. You need to invert matrix A, multiply it by b, you get the solution. Everybody with me?
Yeah.
Any challenges with this that you see with this algorithm?
Can you draw how you multiply inverted matrix on classic matrix?
Because A inverse is just another matrix 2 by 2. We multiply it by...
A inverse is what? Like
First, yeah, of course you need to compute A inverse, but when you compute it, it's 2 by 2 matrix. And you multiply it by B, which is 1 by 2. So it's the same multiplication, just you need to be able to compute A inverse.
Can you give an example of inverted matrix? If A inverse would be what?
So that's another. So algorithm for computing A inverse. So what we know? In order to compute A inverse, this equation should be satisfied. Yeah, you should solve this equation. This is equal to identity with A inverse being unknown. A is known, identity is known. That algorithm is nasty. You can still try to do it, but the algorithm for inverted matrices is nasty, numerically unstable, and you can try it yourself for the 2 by 2 matrix. I'll look at an example in Wikipedia. The thing is, nobody is really trying to use this algorithm to solve the system of linear equations. Because inverting a matrix is unstable, nasty numerical operation. What people try to do instead, they try to use some other algorithms. And the one that you probably heard about is called Gaussian elimination. Anybody heard about Gaussian elimination? So Gaussian elimination is another algorithm where you don't really do invert matrix A. What you do, you try to convert, you first formulate this augmented system. So this is your system of linear equations, 3 unknowns. Augmented matrix is, here is your matrix A, here is your vector B. You put those together. So that's what you call the augmented system. Here you have the matrix A, and after that you have the vector B. And after that, what you are trying to do, you apply linear operations to convert this into the triangular matrix. So by what you do in this case, so you want to create zeros under this. So you want to have 0 and 0 here. So what you do, you take this equation multiplied by 3 over 2, add to this one, so that this plus this will create 0. Yeah? So if we multiply this so that we get by 3 over 2, so you have 3 here, minus 3 cancel out, and you have 0 there. And of course you need to do the same for every. So here is 3 over 2 y minus y. So that's what's going to be 1/2 y. Yeah, so you have 1/2 here. Here is, when you multiply minus z by 3 over 2, you get minus 3 over 2 plus 2. You get something like also plus 1/2 as well, and so on. And you do it with this term as well. So what you do, you multiply this whole equation by 3 over 2, and you add it to this. And the result of summing this up, you write over here. And the idea is to have 0 as the first term. Let's verify this. So that
The inverted matrix, what is the definition?
Sorry?
Definition of inverted matrix is
Yeah, that's the definition of the inverted matrix. The inverted matrix multiplied by itself is equal to the identity matrix. That's the definition of the inverted matrix. A inverted multiplied by itself is equal to the identity matrix. But we are not doing the inversion here.
is equal to
Identity matrix, matrix where you have ones on the main diagonal and zeros everywhere else.
but diagonal is
1,
But you're
top left.
top left to bottom right.
Yeah, the main diagonal. So this diagonal. We can,
But because inversion is so hard, we don't do it.
yeah, so everything which is,
So you just can say, no, you know that it's inversion is hard, don't ever do it, so do these other things instead.
but otherwise, what you know A, you know identity matrix. So the only unknown is A minus. So you need to solve this system, A inverted multiplied by A which you know equal to identity. So you know this, you need to figure out all coefficients of that. And that will be your algorithm for computing A inverse. You need to figure out all the coefficients, all the components of the A inverse, all the components of that matrix. Not a very straightforward easy algorithm because just quite a number of unknowns there. nobody really does that. Even so, you can try an example. Even so, it's not practical. It's not used in practice. So nobody's.
You divide the identity matrix by regional matrix, isn't it?
No. So you need the identity matrix. Sorry.
To find the identity matrix.
No. So here it's difficult because what you have. Let's say it's 2 by 2. So let's say that you have all the matrices 2 by 2. So what you have in the A inverse, you have the 4 unknowns here, here, and there, multiplied by A, where you have 4 knowns, equal to identity, which is 1, 1, 0, 0. So you know this, you need to find this 4. And that's not a straightforward algorithm. You have 4 unknowns that you need to fill out. And this may not be unique.
With small figures it is easy.
No, small figure, but if it's million by million.
Yeah, but it is easy for small figures, but this is not easy even for small figures.
No, this is much easier actually for both. Because you know here what to do in the operations are easy. So what you need to figure out by which number I should multiply my second equation so that when added to this one it creates 0. You need to multiply by 3 over 2. So in that case, 2 and 2 cancel out, you get 3x here minus 3x, you get 0. And let's do this together. So you need to multiply second equation by 3 over 2. So what you get? And after add it to the first one. So let's write the first one and 2x plus y minus z equal to 8. And the second when you multiply it's going to be first. We need to multiply the first one. So we need to multiply this by 3 over 2. When you multiply this by 3 over 2, we get 3x plus 3 over 2y minus 3 over 2z equal to 12. Yeah. And now you need to add this to the second one. So the second one is minus 3x minus y plus 2z equal to minus 11, yeah? So this 3x minus 3x cancel out when you add, so you get 0 here. 3 over 2y minus y, you get 1/2 y. Minus 3z plus 2z, you get minus half z. And here you have 1.
Plus 1/2.
Yes, plus 1/2. Sure. So, and that's what we got. Plus 1/2 y plus 1/2 z is equal to 1. Yeah? As a result, what we created 0 over here. Now we need to do the same with this third equation. So we need to multiply first equation by something so that when it's added to the last one we have 0. And in this case we don't really need to do anything because it's already 2x minus 2x is 0. So we just leave it as is. So here we have 0, here we have y plus y is 2y, minus z plus 2z is just z, 8 minus 3 is 5. So and in this form we created another 0. So we created 2 0 over here, and after it we want to create 0 here so that this is triangular form. Didn't do it at university, no? This Gaussian combination?
Yeah, but it was long time ago.
1990.
Yeah. So basically, even so I don't you to remember this, so the idea is, now we need to do the same. We need to consider these two equations and we want to have 0 underneath. So we need to figure out by what we need to multiply this, such that sum up these two is give us 0. So here we need to multiply by minus 4, yeah? By minus 4. So this gives us minus 2 plus 2 is 0. Minus 4 here is minus 2 plus 1 is minus 1. Minus 4 plus 5 is 1. And now we have also 0 here. So we have the triangular matrix there. And now it's easy to solve. So what you know that z minus z is equal to 1. Or z is equal to minus 1. We already have the solution for z. But there is also even better way. So we do a second step of this to really convert this matrix into the identity matrix. And in that case, you automatically have the answers here. So you do another step. Or you may just stop here and say, okay, we now know how to compute z because minus z is equal to 1. Z is equal to minus 1. Now you can substitute z here and here. You get a smaller matrix. Now you know what is y, and you unroll it back. But there is a kind of more systematic way to do the same. Just now you are going to do the reverse. You are going to start creating zeros above the main diagonal here and there, so that eventually you get the identity matrix here and you get the solution over there. Which is the same stuff as doing this, just more formal. It's called the back substitution. This typically called the Gaussian elimination. And that gives you the solution. Why it's simple? Because you do linear operations. Here, you just multiply by something and add to something at every step, which is very easy. Over here, you need to do much more than linear operations. So we like to do linear operations because those are very stable. Multiplying by numbers and adding to another number, that's very simple. If you want to do something else, even if you want to take the exponent or the logarithm, that's much more complicated. Linear operations, addition and multiplication are the simplest ones and are the fastest on the computer. That's another thing. There is nothing to screw up here. You can do it minute by minute matrix. It's Gaussian elimination. Stable, fast. So used in practice. This is unstable and you need to do much more than this because there are 4 unknowns. If you have there, minute by minute, much more operations and less stability. So, any questions about this? Again, I don't want you to remember all details, that's the idea. All what you need to solve a system of linear equations with Gaussian elimination, linear operations. Multiply by something, add to something. Repeat. Okay? Говорили. Now, next step, why do we need that? Or it's a break? Okay, let's go deeper into deep mathematics. Yeah, my belief is after school you can understand this. It's just a matter of asking me or any other course instructor something that you don't understand. Don't hesitate to ask. Ask as much as you can. In the worst case, I would not know the answer. So what can go wrong? So as somebody said, there are no wrong questions and there are no wrong answers. So that's why we will be.
Will you remember that for the exam?
Exam again. First exam is only 20% of your mark. Second, you are allowed to have a cheat sheet for the exam. So you can have handwritten notes of anything that we have in the slides handouts, so this is more than enough. So it's not open book, but it's the handwritten cheat sheet, 2-sided. So for you, it's a letter-sized piece of paper, 2-sided. For everybody else, it's A4 piece of paper, 2-sided. So it can be 6-sided if somebody can write on the edges. Still, how much time I should put in?
You need to choose a hand font and writing font while printing.
So there's no. 1 hour and 30.
3-point hand font.
So coming back to next step in mathematics. So what we did, we now figure out how to solve linear equations and systems of linear equations. Next big step, how about nonlinear equations? So if I have an equation, nonlinear function is equal to 0. And what's the difference? So we can have linear functions, quadratic functions, and nonlinear. That's what we'll differentiate. So nonlinear function is something like equation like logarithm of x minus exponent of x squared is equal to 0. This is a nonlinear equation. This is a function equal to 0. Yeah? Everybody with me? So linear equations, system of equations are fine already. Now we want to do this as a next step. So how we can design an algorithm to solve this non-linear equation, and let's visualize. So what we have? We have our function f of x, which let's draw it like this, and we need to find this point. This is a point where the function value is equal to 0. This is x, this is the function value, f of x equal to 0, this is the solution. So we want to find this point. Yeah, this is the function. So this, let's call it x star. This is a solution to this equation which we need to find. How we can design an algorithm that will do that? So first, we need to start from some point. And if you have no idea, we start from some random point x0. Any x0 is equal to 25. Any point we can initialize our algorithm. So this is the function value at the point x0. Now, what we want to do? One of the possibilities from this graph. So what we can do? We can try to build a line which is tangent to our function at this point that we start from. So tangent line, find this point x1, everybody with me? And after that, start from the point x1, build another line tangential to a function at the point x1, find point x2, and continue until we find the solution. That's one possibility of the algorithm. So what we do in every step, we replace our difficult nonlinear function with a linear function. And after that, we need to find where linear function is equal to 0. What we need to do is we need to solve a linear equation. After that, repeat. So build another linear function which is tangential to our nonlinear function at the new point, x1, find where it's equal to 0 by solving another linear equation, continue. So what we did, we replaced our difficult algorithm finding a solution to the nonlinear function equal to 0. So by essentially, we replaced difficult solution of a nonlinear equation to a sequence of solutions to a linear equation that we need to find at every point of the algorithm. So we replace the difficult algorithm by a sequence of easy algorithms that we know how to solve. We know how to solve linear equations. Now at every iteration, we know that, we know how we can solve linear equation to find this point, to solve another linear equation to find this point until we converge. And that will be the principle for most of the algorithms. So we replace a difficult algorithm by a sequence of iterations. At every iteration, we solve a simpler problem by using a simpler algorithm. In this case, solving linear equation. In the multidimensional space, solving a system of linear equations. Now, the question is, for that, we need to write down the equation of this line. We need to write down our linear equation. Everybody with me? How we can write the equation of this line? Anybody can tell me? Oh, exactly, the derivative. That's now where we need the derivative for it now. So let's derive the equation of this line. So how we do it? We just will basically draw. So what happens? This line is the approximation of our nonlinear function. What it means that we know in the neighborhood of the current point, this line almost coincides with our function. Yeah? Of course, when we go further, so this is the solution returned by our line, and this is the true, so this is the error. The further we go from the current point, the worse is the approximation. So let's call this point just x. So this is point x, and that's the function f of x that we compute from our linear approximation. That's a function value at the point x0. Now, what we know? So this, let's call this angle alpha. Now, so our function value f of x is equal to, so this is f of x is equal to f of x0, function value at the point x0 plus this distance. Yeah, everybody with me? This function value at the point x is equal to the function value at the point x0 plus this distance. So far, yes, no? Which I will write down. So the function f of x is equal to the function value at the point x0 plus this distance. So what is this distance?
Fx minus fx0.
Yeah, so first, this distance is this distance multiplied by the tan of this angle alpha. Everybody believe me? So this distance multiplied by tan of alpha give us this. Not just the definition of the tan. Tan is this divided by that, and if we rewrite the tan, so this is equal to this by the tan. Tangents in Ukrainian, in English, you know, tan. Have you seen that somebody is saying tangents in English, or is it just tan?
Everybody says just tan.
Yeah, because that's why I tried to figure it out, and nobody knows what is tangents. It's tan. Here it is. In Ukrainian, it's tangents. It's like, you know, you say in English words in Ukrainian, like probability. That's the Ukrainian spelling of the word probability. So, probability. Okay, plus, so the tan of alpha multiplied by this distance. What is the distance? X minus x0. Yeah, everybody with me? This distance is x minus x0. X minus x0. And because we want this to solve this equation, so this is equal to 0. So we just wrote the function equal to 0. Now we still need to figure out what is tan. We need to of alpha. So any ideas what is tan of alpha? Why this line is called tangential to the function? Well, tan of alpha is just a derivative of the function at the point x0. So tan of alpha is the derivative of our function at the point x0. Why? Why, just a definition of the derivative. So what is the definition of the derivative? So derivative is change in the function value divided by the change in the argument, and that's equal to the tan of alpha. That's just a definition of the derivative, nothing more than that. So that's why this tan is the derivative of our function, derivative sign at the point x0, because at this point we calculate the tan. Now what we get? We got this equation, which I'll just, let me rewrite it on a new page. Or no, actually I'll try to fit it here. So what we got? We got f of x0, this, plus the derivative at the point x0, this multiplied by x minus x0 equal to 0. So we got this equation, and this is the linear equation, because the only unknown is x. We know x0, that's just the point that we started. We know how to compute the function at the point x0. We know how to compute the derivative at the point x0. The only unknown is x. So this is actually a linear equation with one unknown x. Everybody with me on that? Because x0 is just a number, function at the point x0 is another number, derivative at the point x0 is another number. The only unknown is x. So this is linear equation. This is actually the equation of this line being equal to 0. So we were able to write down the equation of this line, which is f of x0 plus the derivative at the point x0 multiplied by x minus x0, and we want to find where this line is x0, so equal to 0. Linear equation that we need to solve at the first iteration of our algorithm. Still puzzling? Or you can substitute any function, so we start with x0 equal to, I don't know, 25, substitute here, substitute there, we know the function value. And the only thing which we are still missing, we need to be able to compute the derivatives, because it requires the derivative. But what is the derivative of a function? It's another function. Let's just repeat the rules of the definition. Also the rules of differentiation, so how we computed the derivatives in school. Anybody remember the simple rules of differentiation? So what is the derivative of the exponential function?
X multiplied by f.
It's that function itself. And if you don't remember, just look it up, so no need to remember. So what is the derivative of the logarithmic function?
1 divided by x.
Yeah, if it's a natural logarithm, it's 1 divided by x. One logarithm we need to multiply by a constant, but let's ignore that. So what is x to the power n?
N multiplied by x.
N multiplied by x to the power n minus 1. And that's probably enough for now, for the functions. Now, if you want to differentiate a more complex function, if you have that function that I just wrote, so logarithm of x minus x to the power x squared. So this is our function. So what is its derivative? Let's compute. What is the derivative of the logarithm? We just 1 over x. Now, so what is the derivative of the sum of two functions? Just sum of the derivatives, yeah. So now we need to compute the derivative of the minus exponent to the power x squared. How we compute the derivative of exponent to the power x squared? Anybody remember the chain rule? In Ukrainian it's
It's a
It's a function of a function. So you
yeah, well, let's write it down formally and after we will apply it here. So what is, if we want to compute the derivative of the composite function, so this function which is, if our function
2x
is
squared plus
composite function, and in our case, what is h? H is exponent and g is x squared, yeah? So, yeah. In our case, so this function can be represented as h of g of x. So g of x is x squared, and h is exponent. Everybody sees that? Composite function. Now, what is the derivative of the composite function? So, in order to compute our derivative, we need to differentiate this composite function. And that happens to be the derivative of h multiplied by the derivative of g. That's the chain rule. Which is actually, as we will see on Sunday, that's what is running underneath neural nets. Nothing more than that. The chain rule to compute the derivatives. That's what all neural networks are doing. And we'll do it step by step. So, just to give you an idea. All what neural nets are doing during the training phase is applying the chain rule, which has a fancy name in the neural net settings called backpropagation. But underneath, backpropagation is the chain rule. and again. Don't worry, you'll see it how, but I can give you actually an illustration of that. So in the neural net, so this is our function h, this is our function g, and let's say there was some other function that doesn't matter. Now, so, and this is the output. Here is an input, x. All what you need to know, so y is equal to the function h, which takes additions of the function g of x. So this is how you can write the equation of this neural net. So input x after the function g of x, and after the function h of the previous function, which is h, and this is the output. Now, because you need the derivative of the function, for, as we see for this type of algorithms that I just described, you need to be able to compute the derivative of this term. And that's what it is. So in neural nets, because essentially we work with composite functions, so at every layer we take a function of the previous layer function. That's a composite function, always. Of course it will be even more embedded, because you have also a previous layer and so on and so forth. It will be more loops there. But at the end, because you need the derivative, and exactly of this purpose, derivative is used in the algorithm. So this is what you use to compute the derivative for the neural net, and this computation is called the backpropagation in neural net.
And how many layers will there be in a neural net?
Up to you. You can put as many as you want.
So 4 or 4,000?
I have never seen 4,000, but people have hundreds of layers. That's why it's called deep learning. Actually, the neural net with more than one hidden layer is already called deep neural net. So, and yeah, but it doesn't matter how many layers, so you just gonna to apply this chain rule again and again for the neural net, and that's give you the derivative. But we'll come to that, so don't worry, this is just an illustration why we need this. So now, let's apply this to our function. So what is the function g is x squared? What's the derivative of x squared? 2x, yeah? So 2x, so this is our derivative g prime of x. Multiply by this, the derivative of h. What is h? Exponential function. So what is the exponential function? Is the function itself, exponent to the power g of x, which is x squared. That's all. We just applied the chain rule to compute the derivative of this function. That's the function, derivative of the function g, which is 2x, multiplied by the derivative of the exponential function with the same g inside, so derivative of the exponential function is itself, derivative of the, and here we have the g of x, which is x squared. So chain rule is nothing more than that. Again, we have seen it even in the high school, and I'm sure we have seen it at the university. Just takes time to get used to it, but that's all. How to compute the derivatives of the composite function like this. Chain rule. We also have some rules how to compute the derivatives of the product of two functions, then you multiply one function by another. I think we have written it. The derivative of the function u multiplied by the function v is equal to u prime v plus v prime u, and so on. We have the rules how to compute when we divide one by the other, but we don't need to go that complex, so this is also useful to remember how to compute the derivative of a multiple of the two functions, or of the product of two functions. Okay, so now coming back. So we know now how to compute the derivative, so we can compute the derivative of our function at the point x0, and what's important, the derivative of a function is another function. Everybody understand that the derivative of this function is this function, it's just another function. Yeah? So nothing more than that. So now all what remains to do, because we know how to compute the derivative, is we need to express x from this equation. So we have this equation, we need to express x, the solution of this linear equation. So what is x? X is equal to x0 minus, so it's equal to the f of x0. So that's getting a bit too complex. Okay, if I'm doing it, you can verify me if I'm wrong. Something like this. Am I right? If I express x from this, anybody who can verify? You just unroll this and you get x equal to x0 minus this term divided by this term, if I'm not mistaken. Yeah, and that's it. So that's the computation that we do at every iteration of this algorithm. We start from the point x0, substitute it here, you know everything, compute x1. After that, do x1, 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 compute x2, and we move from one point to another until we find the optimal solution. So this is our algorithm to solve a non-linear equation. Like this. Function f of x, non-linear function, is equal to 0. We substituted it by solving a linear equation at each iteration. So this is a solution of a linear equation. To find x from this linear equation, we just express x. Again, it takes some time to digest. But there is nothing more than visual stuff, function of one variable and the derivative. Yes?
When you put this angle alpha here and not here?
Well, because we do it at the point x0. You see, that's the point from where we start, and that's where we build the line tangential to our current function. We build it at the point x0. And the idea is, it's difficult to work with non-linear functions. It's a non-linear curve, so you try to replace it.
But this angle is the same as this one. So
Yeah,
the
yeah.
angles are the same.
You can do that, but in that case, that's right. But in that case, it's not that straightforward why it's equal to the derivative of x0, because yeah, it's x1. So here, basically, it's more visible why tan of alpha is the derivative of x0, because you do it at the point x0. Yeah, even so, it's the same angle, of course.
And the formula will work if you put alpha.
Well, it's the same angle, of course it will work. Yeah. Okay, so what else I would like to say here? So, and the idea is, so what we wanted to do, in order to design our algorithm, so first, we have to start from any point. And again, if you don't know, we just randomly start from any point. X0 can be any number, which you just randomly generate a number to start. After that, the idea was, we want to approximate our nonlinear function, the red curve, at that initial point by a simpler function. And what is the simplest function is linear. And what is the best approximation is the line tangential to the current nonlinear function at this point, to the given nonlinear function at the current point. That's all. You just do a linear approximation of the nonlinear function. This the idea is that because you're approximating, the function in the neighborhood of the point x0 should behave the same. This linear function should behave the same as our nonlinear function. And as it behaves approximately the same, finding the solution of the linear function is equal to 0, give you some ideas. So x1 is going to be a better point. And after that, you continue building approximation to the nonlinear function at point x1 until you converge to the optimal solution. But the idea is the same. Replace a difficult nonlinear function with a simpler function. The simpler function is linear or quadratic. If you want, instead of approximating the linear function, you can approximate this quadratic function, and as you know, the quadratic function will be closer to this than linear. The disadvantage is for quadratic function, you need to work with a quadratic term. You need to work with x squared, and that's getting more complex, because in this case, instead of linear equation, you'll have a quadratic equation. You may do that, but that's not going to be that much helpful in terms of convergence, and we need to work with a more difficult quadratic function. Even so, quadratic function is a better approximation than linear function, but it's more difficult to work with quadratic functions because you have a second order term x squared.
And because the computer is doing this, you don't care about the number of iterations. Like, it's like
Yeah,
simple.
we'll see how computers are doing that. That's all very common too. So now we know how to solve non-linear equations. What you can do next, it's the same to solve systems of non-linear equations. Just your functions will be not a function of one variable, but the function of two variables, three variables, and the same. So what happens if you need to solve a system of non-linear equations? At every iteration, you will need to be solving a system of linear equations. The formulas will be slightly more complex, but it's the same idea. And we know how to solve system of linear equations, we just discussed that. So basically, to solve a system of non-linear equations, at every iteration you need to solve a system of linear equations, and we know how to solve system of linear equations with Gaussian elimination. That's why we discussed Gaussian elimination. So that was the first step. So we know how to solve non-linear equations and systems of non-linear equations. Now let's do it. Let's take it to the next step. How we can find the minimum or a maximum of a function. Another typical problem in data science, and that's a problem that powers all machine learning, neural nets and stuff like that. So we want to minimize or maximize a function. Slightly different problem. Before that, we were solving this equation. Now we want to minimize the function. Let's see actually what we can do. First thing, does it really make any difference if I want to minimize a function or maximize a function? Are those two different problems or not really? No, that's actually the thing is maximizing the function is equal to minimizing -1 multiplied by that function. Why? Well, let's plot. If you don't understand, so maximizing this function, that's the point of maximum, -1 multiplied by this function is this. Yeah? We just do the flip over the horizontal axis, and as you see, it's the same solution over here, the same optimal solution, x star. So maximizing f of x with this solution is can be replaced by minimizing minus the function f of x and give you this solution, but the same solution. Everybody sees that? So that's why people don't differentiate minimizing and maximizing, because maximizing can be always replaced by minimizing -1 multiplied by that function. Those are equivalent, so people always write it this way. Okay? Don't consider two cases separate, minimize and maximize. Now, if I want to minimize this function, this is the point of minimum. So what is the property of this point of minimum? If we put a line tangential to that function at the point of minimum, what is the angle? 0. So tan of 0 is what? 0, of course. So derivative should be equal to 0 at this point, because the derivative is the tan between angle and the horizontal, and this is already horizontal, so the angle is 0, tan of 0 is 0, so the derivative at the point of minimum is 0. So what that means, that in order to find this point, you need to solve an equation, the derivative of x is equal to 0. Everybody with me so far? What we also know, that derivative of a function is not a function. So what that means? That's a non-linear equation. And how to solve non-linear equations? Well, we just did that. This is the algorithm on the previous flip chart, which is known as the Newton method. I just forgot to mention that. So this is a non-linear equation applied to another function, because derivative of function is not a function, and we know the algorithm how to solve it. We know even the formula. So the formula to solve this non-linear equation is to find the next point, we take the previous point minus the function value divided by the derivative of that function. Yeah, this was the algorithm to solve this. Now, how we design the algorithm to solve this? The question is, can we use this algorithm to solve this non-linear equation? Can they use the same algorithm? Actually, it's as simple as taking f and replacing it with the derivative, taking the first derivative and replacing the derivative with the second derivative. All what I need to do, take this formula and replace function f with its derivative. Because now we are applying this to the function f prime instead of function f. Well, let's do that. So let's x1 is equal to x0 minus the derivative of the function at point x0 divided by the derivative of the derivative, which is second derivative at the point x0. Very easy. Now we have the algorithm to minimize the function.
And x1
which is essentially the same algorithm.
And x1 in this sense is what?
Is the next point, and after it we continue. So what we do next, so to compute x2 is equal to x1 minus at the point 1, and so on. And to compute x3, you apply this to the point x2, and so on. So you just iterate coming from the previous point to the new point. Starting from point x0, it's all 0, we compute the next one. After we start from point x1, we compute point x2, and we continue. So, question about this. So this is called the Newton method for solving non-linear equations. This is called the Newton method for optimization. For solving an unconstrained optimization problem, no constraints, just minimizing function f of x. The thing is, in order to apply this Newton method to minimize the function, we need to be able not only to compute the first derivative, but also to compute the second derivative, yeah? Because it's over there. But the second derivative, we compute the first derivative, after differentiate the first derivative one more time, then we get the second derivative, it's another function. No problem with that. So any question so far? Okay, good. So Newton algorithm, that's how it's called. Newton algorithm for solving systems of nonlinear equations, Newton algorithm for optimization, the same algorithm. Just apply it to the function or to its derivative.
But on the previous slide, we found
Click. Yes.
we found this point also by iteration.
Yeah. So we find x1, and after that we apply this to x1 to compute x2. And I said here, so and we continue until we stop. That's another thing. So we find, knowing, starting from any x0 we find x1, after that, starting from x1 we find x2, and so on until we stop. The big question, when do we stop? And here there are a couple of choices. So first, when you see that this difference, so going from previous iteration to the next iteration is getting very small, because you say, if it's less than 10 to the power minus 6, I stop. That's the simplest. The same you may use at the decrease in the function value, the difference between the function value is 0. So when this decrease is getting small, you just stop. Or you can combine two, so decrease in x and decrease in the function value itself.
It's called convergence, yeah?
It's called convergence, yes. So basically, that's called the speed of convergence. And in this case, it's pretty good. It's quadratic. We will see why. But the price that we need to pay for that is computing for optimization. If you want to achieve this convergence, you need to compute the second derivative. And we'll see later on, can we redesign this algorithm in such a way that the convergence is not as fast, but we don't need to compute the second derivative. That will come next, when we completely understand this. So next step, how about function of more than one variable? If we have function x, not only of x, but x is a vector, x1 and x2 for instance, two coordinates. Now we'll need to refresh our knowledge about the partial derivatives. And this is when we have this handout. So let's go and refresh our knowledge about the function of, functions of more than one variable. So what we have? If we have a function of more than one variable of the vector x, which has coordinates x1, x2 to xn, so that's a multidimensional function of more than one variable. Everybody has seen that. Yeah? Now, how we do derivatives? In this case, we need to compute partial derivatives. We can compute derivative of that function with respect to x1, after derivative with respect to x2, partial derivative with respect to x3, and so on. Those are called partial derivatives. And as we have seen those potentially as well. And now we can put those in the vector. So the partial derivative of the function with respect to x1, the partial derivative of the function with respect to x2, and so on. And that vector is called the gradient of our function. It's denoted as this triangle f of x, and this is just a vector of the first partial derivatives with respect to x1, x2, and x3. So what do we do to compute the partial derivative with respect to x1? We treat all other variables, x2, x3, and so forth, as constants, as just numbers, and compute the derivative. The only variable in that case is x1, when we differentiate with respect to x1. That's it. All others are numbers. And we'll see the example on the next page, so I'll just postpone the example to compute the gradient. So this is called the gradient or the vector of the first partial derivatives of our function with respect to each of the variables. So each coordinate of that gradient vector is a partial derivative with respect to x1, x2, and so on, up to xn. Everybody with me so far? Kind of. You've seen that? Kind of. We'll do it for the function of two variables to see it more precisely. Actually, let's do that immediately. It's on the next page of the handout. Let's compute. So this is a function of two variables, x1 and x2, x1 squared minus 3x1 x2 plus x2 squared. And we want to compute its gradient at the point 1, 1, and after the matrix of the second partial derivatives, but that's postponed. So, what we do to differentiate this function with respect to x1? So x1 squared differentiated with respect to x1 is what?
2x.
2x1, yeah, we put it here, 2x1. Minus 3x1, 2. So when we differentiate with respect to x1, we treat x2 as constant, it's just a number. So what's the derivative of minus 3x1, x2 with respect to x1?
3x2.
Minus 3x2. Minus 3x2 because we treat x2 as a constant, it's just a number, it's not a variable. So it's going to be minus 3x2. When we differentiate x2 squared with respect to x1? x2 squared is just a number. So what is the derivative of a number with respect to the variable?
0.
0. That's why there is plus 0. And we put it here, and this is the derivative of this function with respect to x1 is 2x1, as we said, minus 3x2. Should I make it bigger? Now let's differentiate this function with respect to x2. x1 squared differentiate with respect to x2 is what?
0.
0. Minus 3x1 x2 with respect to x2 is
3x1.
minus 3x1. x2 squared with respect to x2,
2x.
2x2. So here we got our gradient vector. That's a vector of the first partial derivatives. And because we want to compute the gradient at point 1, 1, x1 is equal to 1, x2 is equal to 1, substituting 1 here, so 2 minus 1 is minus 1, 3 plus, minus 3 plus 2 is minus 1. So the gradient of that function at the point 1, 1 is minus 1, minus 1. This is the first partial derivative with respect to x1. At the point 1, 1, this is the first partial derivative with respect to x2 at the point 1, 1. Take some time, so no rush.
I have no intuition about what that means. So what does that gradient mean?
That's what will come next. Gradient is a vector. Well, it's a vector with two coordinates. So if you want to plot a vector in a multi-dimensional space, let's say that, let's start with this. So this is x1, this is x2.
Sure, so it's 1, 1.
And you want to plot the vector, let's say the gradient is equal, let's say 1, 1. Or in our case, okay, let's plot it directly minus 1, minus 1. That's what we plot. So when you plot minus 1, minus 1, what you do? Here is 1, 1, minus 1, minus 1. So if you want to plot this vector minus 1, minus 1, how you plot it?
Sure, minus 1, minus 1.
Exactly, you start from here, from 0, 0, things. So here is minus 1, minus 1. This is the visualization of this vector. Of course, you can move it anywhere. So you can, if you start from this point, this is the same, which is there. Yeah.
Yep. So it's kind of like a slope of the.
Exactly. So
Yeah.
what is the gradient vector? Is the vector with first partial derivative.
The slope.
Each partial derivative is the slope with respect to that vector. When we looked at this, basically, so what we said here, we compute the tangential line. Tangent of alpha is the derivative, and that's the slope. So tan of alpha is the slope. So what is the slope here in this point? Positive or negative?
Positive.
Alpha is the angle which is between 0 and 90 degrees. So what is the tan of an angle which is between 0 and 90 degrees? Is positive or negative?
Positive.
Positive. So that's a positive number. If I do tan here, so in that case this is the angle alpha, which is more than 90 but less than 180 degrees.
Negative.
It's negative. There's a negative slope here, positive slope here. Now, how do we represent that as a vector? In this case, it's of course one-dimensional, so the gradient is just a number. That's in this case because the function is a function of one variable. So positive slope. So what is a positive vector? How do I plot the positive vector here?
0.5.
So this is a positive vector, yeah? And this is a negative vector. Everybody with me? Cool. So we can do it for one-dimensional functions, we can do it for multi-dimensional functions. So in this case, of course, I need to add the dimensionality for the function itself. So when I'm going to plot this, let's use the next slide because we'll come to that in any case. And let's pretend that this is our function, that's a quadratic function. I'll try to plot it approximately. With my plotting capabilities in 3 dimensions, which are okay but limited. x1, x2, and here is the function value. Y is equal to f x1, x2. So that's quadratic function, so we know that quadratic function looks something like this. Yeah? Everybody with me? So now we want to compute the gradient at point 1, 1. Now 1, 1 is, let's just make it up. Sure. So let's say this is represented here, so it's a function value at the point 1, 1, which is here this, and after that its gradient is -1, -1, which is, okay, this is somewhere, something like that, yeah? I guess. So that's what you represent. So the gradient shows you the direction in which function, what is doing? Increasing or decreasing?
Increases.
Yeah. Moving.
Moving, that's okay. Now we want, so is it this vector, which is a gradient, is it pointing to a direction where the function value increases or decreases?
Increases.
Increases. We also have seen it here. So here, the gradient is pointing in this direction at this point, so the function grows or increases in that direction. Yeah? Here, the gradient point is here, so function increases. How about gradient multiplied by -1? Oh, that's the opposite. So if you multiply gradient by -1, it shows the direction which function is decreasing. So this multiplied by -1 gives you this function is decreasing in this direction starting from this point, and vice versa. So that's another interesting useful thing. Direction of the gradient shows you the direction of the function increase, direction of the negative gradient shows you the direction of the function decrease. So this is the gradient multiplied by -1 at our initial point at 0. How we can use this?
You want to slide towards the 0.
And that's actually, that's useful. That's a useful direction. So, if we want to minimize your function, we want to go in the direction of the function decrease from the current point. For instance, we can use it in the direction of the negative gradient. Because we know that the function is getting smaller in that direction. Our goal is to minimize. Of course, that's a useful direction for us to do. Moreover, this direction is known as the steepest descent direction. That's why the function decreases with the highest speed. And of course, the positive gradient itself is the steepest ascent direction. That's the direction which function increases also with the highest speed. Useful directions to know, which we'll be using later on in the algorithms as well. Because if you want to minimize the function and you start from point x0, probably it makes sense to go in the direction of the negative gradient because the function is getting smaller. But the problem is, if you go too far, you see, I started from this and I went too far. Function already starts. I went too far. You see, function already starts increasing in that direction. If I went too far, if I went like that far in that direction, if I went just a small distance, you are not moving too much. So it's useless because you are staying pretty much at the current point. So in addition to knowing the direction of the function decrease, you need to know how far to go in that direction. And the restriction is you don't want to go too far and you want to have a too small step. That's actually another, so as we started talking about, that's another algorithm for minimizing the function. Another algorithm is, how it's called? Basically minimizing the function. So the first algorithm that we have written is this algorithm for minimizing the function. We take this step, and for now let me rewrite it actually in the for the functions of not only one variable but the multiple variables. So this is Newton method for minimizing a function in order to move from the point x0 to the point x1. That's the format written. So we need to take the divide by the second derivative, but because now the matrix of the second partial derivatives is going to be the matrix, so we need to take the inverse, multiply by the gradient of this. So in the notation of scalar is x0 multiplied by the first derivative divided by the second derivative. Then we have just the function of one variable. If it's function of more than one variable, we still multiply by the first derivative, by the gradient, but we need to divide by the second derivative, but the second derivative is a matrix, so instead of divide, we are taking the inverse. So this is a formula for the same Newton algorithm applied to the functions of more than one variable, and we still need to be able to compute this matrix of the second partial derivatives. But as soon as we know how to compute it, this is our algorithm for minimizing a function of more than one variable. But what we also just said, and you probably need to repeat it a number of times, now you remember, you need to compute this matrix of the second partial derivatives. That's complex by itself. Now you also need to invert it. We don't like to invert.
No.
So can we do something else? Can we do a simpler algorithm that is not using second derivatives, it's using the first derivatives? And we just said that yes, if we replace this by a number, so if I write down this, let's call it a number alpha. So if I write down this equation, x0 is equal to x1 is equal to x0 minus alpha multiplied by the gradient, just replacing this second derivative with the number alpha, That's exactly this idea. So we start from the point x0, we move in the direction of the negative gradient, minus 1 multiplied by the gradient, and this alpha tells us how far we should move. Should we move that far, that far, that far in the direction of the negative gradient? Which gives us another algorithm for optimization of the function, which is called the gradient descent, or steepest descent. Yeah, that was the first algorithm, Newton algorithm, but its disadvantage, it uses the second derivatives, it converges fast, that's the advantage. Here, in a simple algorithm where we disregard this gradient completely, but we still move in the direction of the negative gradient. You know, that's a good direction because the function is getting a small direction. Just we need to figure out how far to move. 1 unit, alpha equal to 1, 2 units, 0.5 units. So alpha will tell us how far to move in that direction. We somehow need to compute it. So this algorithm is called the Newton method. Yes. And this is called the steepest descent, or gradient descent. Also called gradient descent, or steepest descent. So, again, what remains to figure out how to compute this matrix of the second partial derivatives.
And just have 10 minutes before I break.
Okay, let's finish with calculating the Hessian matrix of the second partial derivatives, and after that, let's try to put it together one more time. So, matrix of the second partial derivatives, this matrix where here you put the second derivative with respect to x1, here you put the derivative with respect to x1, after that x2, and so on. So all combinations is called the Hessian matrix. It's a matrix of the second partial derivatives, where you first differentiate with respect to first variable and after that with respect to the second variable. On the diagonal, you differentiate twice with respect to the same variable. So here you differentiate twice with respect to x1, here you differentiate twice with respect to x2, and so on. And on the other diagonals, you differentiate with respect to x1 and x2 because it's a first row, second column, and so on and so forth. One first observation is the order of differentiation doesn't matter. Everybody remembers that? It doesn't matter if you first differentiate with respect to x1 and after with respect to x2, or first with respect to x2 and after with respect to x1. So that's why this matrix is going to be symmetric. So this is going to be the same number, because differentiate with respect to x2 and after with respect to x1 is the same as differentiate with respect to x1 and after with respect to x2. So Hessian matrix of the second partial derivatives is quadratic and symmetric. It has dimensionality m, the same as number of variables, and is symmetric matrix. We still need to compute it if you want to apply it here in the Newton's method. So that's, and yeah, on the next page, that's an example how we compute the Hessian matrix, and after that we'll try to put it all together. So for the same function, we computed the gradient, the vector of the first partial derivatives. Now we need to compute the Hessian, the matrix of the second partial derivatives. And so the first component here is the second derivative with respect to x1. We have the first derivative with respect to x1. Now we need to differentiate this one more time. So what will be the derivative of this with respect to x1? 2x1 differentiate with respect to x1 is what?
2.
2 minus 3x2 differentiate with respect to x1 is what?
0.
0. So that's why we have 2, we put it here. Now we need to differentiate with respect to x1 and after with respect to x2. So this is derivative with respect to x1, now differentiate with respect to x2, and we get minus 3. Yeah? Everybody with me? Now, here we need to take the derivative with respect to x2 and differentiate with respect to x1. So this differentiate with respect to x1 is minus 3. As I said, it's symmetric matrix. As expected, the order of differentiation doesn't matter. And here we need to put the second derivative with respect to x2. So this is first derivative with respect to x2, differentiate one more time, we get 2, we put it there. So this is a Hessian matrix of the second partial derivatives for this function.
But it's symmetric only because we had such type of function, or it would be all the time symmetric?
Yeah, so the stopping.
We want you back to the first.
To that room, right. Okay, so we can just stop and move to that room.
I want to answer this question though too.
Yeah, of course. Let's finish what we are talking about and we'll move in like 5 minutes, yeah?
The matrix is symmetric because we had this type of function, or it will be symmetric?
It will be always symmetric. Because the order of differentiation doesn't matter for any function. That's one of the rules of differentiation. Differentiating with respect to one variable, not with respect to another, is the same as differentiating in the opposite order.
So this is the nature of the matrix.
That's the nature of differentiation. Yeah, Hessian matrix is always symmetric.
Second.
That's right.
Second.
And symmetric means if you flip it along the main diagonal, the same matrix. That's what it means. So if you flip it this way, you get in the same matrix. Yeah, that's what symmetricity means. So the numbers above and below the main diagonal are the same. Yeah.
About this issue when we can miss the minimum if we will go too fast. So we can miss the minimum if we apply alpha approach, but we will never miss if we apply Newton.
We will again, there are some convergent properties, and for convex functions it will always converge. And we'll discuss what is a convex function, how to check if a function is convex, and why it's important. Yes. For this, because there is no parameter, so alpha is a parameter that you need to choose yourself for your algorithm. Because here there is no parameters, it will do it by yourself.
And these are for all unique minimums.
It's for how to phrase it in a better way. Unique minimum is
for this part of function.
Again, so even if it will do for this function, so this is also unique minimum. Even so, this is the whole range of x's, but because the function value the minimum is unique, yes, it works for this. It's still the unique minimum, just it achieved for this x, and that x. It will still work for that, yeah. If you have function like this, and we'll come back to that, so it will depends where you start from. If you start from this point, it will converge to this minimum. If you start from that point, it will converge to that minimum. Yes, it will find the minimum. If it's unique minimum, it will find that unique minimum. It will find. If there are multiple local minimas, depends of your point x0 from which you start your algorithm.
And there's no way to just that for us to know that.
We will do our best. That's we need to understand. And this is the whole thing of the data science. We are working with functions, so you need to understand which function you are trying to minimize and the properties of the functions, and that's where we are kind of grading. You will need to understand the properties of the function that we want to minimize. So far, okay, two algorithms summarizing. This is the Newton algorithm. The disadvantage is it uses a second derivative, so you need to calculate the Hessian matrix and invert it. Actually, very strict. You don't need to invert it. You can solve a system of linear equations, which is still possible, because remember, this has now very familiar form. A inverse multiplied by B. That's a solution of the system of linear equations. And we can rewrite it as x multiplied by x equal to B, and we can solve the system of linear equations. So there is a trick. But still, you need the Hessian matrix. Even so, you don't need to invert it. You need to solve this big system of linear equations. Over here, it's simpler, but you need this parameter. It has slower conversions. And there is also an intermediate algorithm where you can, instead of computing the Hessian matrix, you can compute this approximation, H, which there are special algorithms to do that, and those type of algorithms are called quasi-Newton. Quasi-Newton because they're not computing the Hessian exactly, they are replacing it by some approximation matrix H, which has some special properties, and I'm not going to discuss how to compute it. Just if the gradient is computed exactly, it's Newton algorithm. If the gradient is approximated, it's quasi-Newton algorithm. If there is no gradient, but there is this step length alpha, so this is the gradient descent. And as always, there are advantages and disadvantages. This is fast convergence, but you need to compute second partial derivatives. This is slow convergence, but you don't need to compute second partial derivatives. The thing is, all these algorithms need the first derivative, need the gradient vector. Gradient, gradient. All optimization algorithms that we will be using, pretty much, and that's all optimization algorithms used in machine learning will need the gradient. And that's why we're talking about the derivatives, because those are used in the optimization algorithms. Every optimization algorithm will require you to supply the derivative. So you need to supply a function in Python that computes the gradient vector, the vector of the first partial derivatives, in addition to the function itself that you are minimizing. That's what it is, because it's used in the algorithm. So derivatives are not for fun, as we were taught in the high school. Derivatives are used in optimization algorithms, and that's what powers machine learning.
They also surprises.
Yeah, derivatives are not for fun.
No.
T-shirt.
Exactly. Oh, as they say, there is this fun T-shirt from NASA. It says better than average, but the average is a formula. So it says better, and after the formula to compute the mean. Better than average, if you read it besides. So, any other questions before we move to the more flexible room? Do we need to make photos of all these things?
But we have it in the presentation.
Not everything. So I try to make it more fun, because if you just look at the slides you get bored and you fall asleep. So I try to put some things on the board. Yeah, formulas are there, but the visualizations are not there.
Did you make photos?
I think I have everything, but
Maybe
they're still here.
You can send
Let me check if I have them all.
Yeah, we can post those on,
Telegram.
Yeah, we have a group.
even on Moodle. So
Yeah, that will be the best.
we need this interactive board where you can save the images directly and just post those. Okay, that's getting complex, but hopefully not overly.